Good morning, everybody, and welcome to the second day of CoRL. It's my great pleasure this morning to introduce our second keynote speaker, who is Dorsa Sadik from Stanford. So Dorsa works in human-robot interaction. She's somebody who thinks deeply about models of systems, and she comes from a background where she's been interested in formal verification of systems. So she approaches this problem of human-robot interaction from a background of thinking about probabilistic modeling and verification, where she's made some deep contributions to linear temporal logic specification, in particular probabilistic signal temporal logic and chance-constrained temporal logic. So she, from the very beginning, when she started working on these research problems, she was interested in human behavior. She worked in human interface design, working on projects in human driver behavior. And then these kind of directions came together as she started thinking about models for how humans interact with robotic systems, and then how one might design robotic systems to work well with the people they have to work with. As she's developed her lab at Stanford, she's got a number of exciting projects in robotics, both autonomous cars and personal robotics that work, for example, in co-manipulation tasks, where she and her students are working on projects related to information gathering over human internal state and preference-based learning of reward functions. So Dorsa got her PhD at Berkeley, and since September 2017, she's been an assistant professor in computer science and electrical engineering at Stanford. She's won a number of awards, including the AFOSR Young Investigator Award, the NSF Career Award, research awards from Google and Amazon, and a large number of Best Paper Awards and Best Paper finalists. So, for example, she is one of the finalists. You heard the announcement yesterday morning. She's one of the senior authors in the Best Paper Award finalist for this conference, which you'll hear that paper a little bit later this morning. Also an award finalist for RSS, HRI, all this year and last year. So congratulations, Dorsa. So it's a great pleasure to introduce Dorsa, and Dorsa, take it away.
Thank you so much. Thanks for the kind introduction, Claire. And yeah, thanks for inviting me. Really excited to be here. So let me start sharing my screen. Everyone can see it? What's up? Yes. Okay. All right, so let's get started. So yeah, I'm Dorsa, and I work on algorithmic human-robot interaction. And today what I'd like to do is, I'd like to walk this boundary of robot learning and human-robot interaction to try to understand what robot learning can do for human-robot interaction, and also like what can we learn from interactive autonomy for robot learning in general. So what is that boundary? How can we do that better? So if you think about the field of robotics, over the past decade, we have seen a lot of advances in this field, and we have finally got to a point where we can think about intricate and long-term human-robot interactions, right? Like we see this in autonomous driving, as autonomous cars are interacting with human-driven cars or pedestrians, and we're starting to see this as robots are entering our homes, like when we have service robots or where we have assistive robots trying to help us feed ourselves. But still, there are quite a bit of challenges here. And I think one of the big challenges here is thinking about that interaction between the robot and the human and trying to make that as effective and as seamless as possible, just like how humans do it. So if you think about human-human interaction, humans are amazing at this. They easily come to each other's spaces, and they collaborate and coordinate with each other on complex manipulation tasks. And a good question to ask is, well, how is it that humans are able to do this? How should we model even human-human interaction? So let's think about that for a few seconds. So imagine that we have two humans that are coming together, trying to do a task together, a collaborative task, or maybe a competitive task. Let's say these two people are trying to play a game of chess. So one way of modeling this interaction is to assume that each one of these agents is going to have some model, some representation of the other agent. Basically, it's going to have some model of how this other agent is going to play on this game of chess. And you can even go further and think about the fact that this opponent is going to think about us thinking about them. And we can kind of like have this infinite regress of recursive reasoning of me thinking about you, thinking about me, thinking about you, right? And that's often referred to as theory of mind in human-robot interaction or in robotics in general. So this idea is not also common to robotics. This shows up in a variety of fields, right? In reinforcement learning, this is called opponent modeling. In natural language processing, this is often referred to as pragmatics and rational speech act. And in general, in all of these fields, like people have realized that if you want to do full-on theory of mind and full-on game theoretic modeling, it turns out to be particularly expensive, this type of recursive belief reasoning. So what ends up happening is that people have approximations of this. Instead of doing the full game, maybe they cut it at the nth time step and they do nth order theory of mind. So this is also common in human-robot interaction, right? Like maybe doing first order theory of mind, where we assume that there's a human and the human has a model of the robot. And at the same time, maybe the robot has some sort of model of the human and they come together and we think about coordination based on that. This is an idea that we have actually used in an autonomous driving setting. So in an older project, we looked at how we can plan for an autonomous car based on this type of game theoretic reasoning, based on having models of the human. And we were able to, like thinking about this full system of human and robot interacting with each other, we were able to get very interesting behaviors. For example, we were able to get behaviors where an autonomous car kind of acts like this white car here, and it starts nudging in front of other drivers and kind of like make them slow down, make them respond, which is pretty interesting. It's a very interesting interaction that you would get here that you wouldn't normally get if you weren't thinking about this type of interactive behavior. And I want to emphasize, this is beyond coordination. This is not just coordination between the two cars. What ends up happening is that the white car here is influencing the other agent and making the other agent slow down, right? Making that other agent to not go 60 miles per hour anymore, which is a pretty interesting point. And the reason I'm emphasizing it is I'm going to come back to this idea of influencing later on in the talk. But going back to our theory of mind story, I think this idea, this perspective kind of works out nicely in a variety of human-robot interaction settings. But the thing I would like to argue is that a lot of interactive tasks are also not like playing chess. Actually, a lot of interactive tasks are kind of like this. Like you have two people coming together, like Alex and Bob coming together, trying to build an object together. In this setting, I really don't think Alex is thinking, well, I wonder what Bob's belief of the world is or what Bob's belief over my policies are. Like, I think something simpler is happening here. Like, one thing I know about humans is that they're bounded rational and they're not going to be able to capture these high dimensional beliefs, right? So I think what is happening here is people are keeping track of a much lower dimensional representation that is almost sufficient for doing the task. That's a shared representation based on the task and is enough for achieving the task. And humans are really good at picking up what that is. And you even often have names for it, right? Like we call it roles, like who is leading, who is following, or we call it intent or goal. And you might be asking, well, what is the big deal here, right? Like people have done belief modeling over goals and intents like over the years. Like, why am I making a big deal out of this? Well, this is actually different. Like what I'm proposing here is not necessarily having a set of intents and trying to do belief modeling on that. What I'm proposing here is trying to figure out what that shared representation even is, right? Like without having any prior knowledge of that. And how is it that humans are able to figure that out like fairly quickly? So going back to this idea, like this is a core idea that I'm gonna come back to throughout the talk in general. This idea that in general, when we have interactive tasks, there is this orthogonal perspective to theory of mind, which basically says, well, don't worry about modeling everything about the other agent. Maybe there exists some low dimensional shared representation that can capture the interaction here and that you can use for coordination and collaboration. And even you can maybe go further and use that for adaptation. The fact that that person changes over time, maybe you can capture the fact that that person changes and the non-stationarity of the other agent using this low dimensional representation. And mathematically, this low dimensional representation is fairly similar to some notions of sufficient statistics, right? Like what are the things that are needed for achieving this task together? So having that in our mind, right, like going back to this example of two agents coordinating, I think there are a few points that are kind of important here. One is the fact that, well, there's this person, Alex or Bob here, and both of them are changing and they're non-stationary, right? Like they're learning, they're getting better at the task. And we can't assume that they have some sort of fixed reward function or policy, right? Non-stationarity is actually a challenge here when we're actually thinking about coordinating with people. The other point that I think is important is if I'm trying to build a robot that coordinates with Alex in the same way that Bob is coordinating with Alex, I should be thinking about how that robot can coordinate, collaborate, and further maybe influence, kind of like the car example I was mentioning earlier, right? Like in this case, the white car was influencing the other driver to make this coordination happen. And it was for this better good of like doing this merge maneuver. But maybe the robot has some sort of objective, and based on that, it could influence and coordinate. And then furthermore, I think this latent representation, this idea of figuring out what is that core that we need to capture from the interaction and use that for better coordination is kind of useful and important view for achieving this task. It's a perspective on trying to do better coordination. So with that, my plan today is to talk about three main topics, three vignettes that try to capture some or all of these ideas of non-stationarity, coordination or influencing, and this idea of using latent representations. So I'm going to start talking about learning latent intent or latent strategies during coordination. Then I'm going to switch topics and think about it from the perspective of learning from interactions, learning from humans, and talk about learning reward functions. And for the last section, I'm going to talk about learning latent actions for better coordination. All right, so let's just get into it. So going back to this example, I really think when we are interacting with other agents or humans are often non-stationary, and they tend to update their behavior in response to the robot. And ideally, we would want to be able to capture that. Let me give you an example here. So imagine we have two robots coming together. We have an ego agent, which is on the left. This is the robot that we are trying to plan for. This is our robot. It's a learning agent. And then on the right, I have this other agent, which is this other robot. And this other robot is following some rule-based policy, like going to the left, pushing the puck to the left, or pushing the puck to the right, or pushing it to the center. And yeah, we're playing game of air hockey here. So imagine that these two robots are trying to play this game of air hockey together. So then an interaction is going to be a sequence of state and actions and rewards from the perspective of the ego agent. If the ego agent is getting a reward or not comes into this interaction. And then if you think about this other agent, if it pushes the puck to the left, and let's say the ego agent blocks it, it's going to change its policy and then push the puck maybe to the center because it might think that the ego agent is good at blocking on the left. And then it follows some sort of dynamics, and that dynamics is this F dynamics, which is based on the previous value of its state, which is Z, and also the interaction that it sees. And the idea is that the ego agent here doesn't really have access to this F. It doesn't know how this other agent is changing its strategy. The only thing it observes is just that interaction and the reward that it gets. So the question that I think is interesting here is, how can we model the other agent? And the way we go about it here is by collecting these past interaction and trying to encode that to a low-dimensional representation, a latent strategy. We call this a latent strategy that is able to predict the next interaction. So the way we are training this latent strategy is using this autoencoder based on the past interaction. We are trying to capture the core that is able to help us predict the next interaction. And this basically captures, like in a sufficient manner, how the other agent is changing and responding to our actions. So now that we have this latent representation, now that we have this latent strategy, what we can do is we can basically plan for our ego agent. We can do reinforcement learning for our ego agent. And the way we do that is by maximizing the expected return of the ego agent. But this reward function now is going to be conditioned on the latent strategy, on the fact that this other agent is changing, and then now we know what that representation looks like. So if we maximize this expected return within an interaction, what ends up happening is that we end up being able to get a policy for our ego agent, being able to react and collaborate and coordinate better with the other agent. And this is actually a CoRL work, and Annie will be talking about this immediately after this talk. And we call this algorithm Lily, learning and influencing latent intent. So let's see how Lily works. So let's go back to this air hockey example. So if the ego agent blocks the puck, we are getting reward of +1. We're saying, well, the ego agent is going to get a reward of +1. And we are designing this experiment. So if the ego agent is blocking the puck, particularly on the left, then the ego agent is going to get a reward of +2. Maybe it is easier for the ego agent to block it on the left. So you're designing it so you get higher reward if you go on the left and block it on the left. Okay. So if you use state-of-the-art reinforcement learning, like soft actor critic, what ends up happening is after starting with an initial policy and then training it for, let's say, 2 hours, our ego agent is able to learn a policy that blocks the puck only in one mode. So for example, in this case, it learns to go to the right, and that's the only thing it learns. Because again, it doesn't model anything about the other agent, so it just like gets good at one of these modes. And at some point, it might realize that, well, actually, going to the left is better because I'm going to get a higher reward there. I get a reward of +2. So finally, after 4 hours of training, it's going to realize that, and it's just going to go to the left and always go to the left. And by always going to the left, basically, soft actor critic is able to block the puck like 40% of the times. So this is actually a plot of success, not reward. So what ends up happening is soft actor critic starts blocking it on the right, and at some point it switches and always blocks the puck on the left, getting like 40% success. Okay? So what happens if you use Lily? So if you use Lily after 4 hours of training, our robot is able to block the puck no matter where you push it, because it does model this latent strategy. It captures how the other agent is changing. And in terms of success rate, we are going to be around 90%. So 90% of the times we are blocking the puck because we are capturing how the other agent is changing and how we should coordinate with the other agent using this representation. Okay, so that's all great, but we could even do better here. So going back to this formulation, right? Like this allows us to react to the other agent. But what if you want to influence the other agent, right? Like I know blocking the puck on the left is better for me. That's going to give me a reward of +2. Can I influence the other agent to get the puck always on the left? So the way we do that is actually, instead of maximizing the expected return within an interaction, we maximize it across interactions. So we consider a more global view. So the ego agent, from a global perspective, maximizes the expected return over all these interactions, and that allows us to actually influence the other agent. So using this type of policy, Lily with influencing, in terms of success rate, we are actually doing fairly similar to Lily. Like we are going to get like 90% success rate. So if you push the block any direction, it is going to block it. And this is actually the success rate plot. So it kind of like looks similar. But the thing that is different is using Lily with influencing, we are actually going to be able to get the puck on the left more often than normal, right? So we would be able to influence the other agent to push the puck to the left like 41% of the times, as opposed to like uniformly getting left, middle, and right, where we get in the no influence scenario. All right, so what is the key takeaway here? So I've been basically talking about the fact that human partners or other agents, other partners that you're coordinating with, they're often non-stationary. And then we should try to capture that non-stationarity. And one way of doing that is by capturing that using a low-dimensional latent strategy. And what Lily does is it anticipates this partner's behavior using latent strategies in order to react and influence to the other agent, which is kind of nice. But the thing I want to emphasize here is, at the end of the day, I'm very interested in getting these robots coordinating with people, right? Like actually having a person in the loop. And we actually tested Lily with humans in the loop, and we had some promising results. But when it comes to training with humans, it's incredibly difficult to bring in the human in this training loop, right? Like train this reinforcement learning with data where we are collecting from actual humans. And if you don't do that, like that makes our policy fairly brittle when we are interacting with actual humans. So the thing that is difficult is that if I want to bring in humans and interactions with humans and try to help robot learning based on interactions that I'm getting from humans, that ends up being fairly expensive and impractical at times. So going back to this diagram and what I've been talking about, basically I've been talking about this idea that there are evolving interactions and there are non-stationarities, and we could capture that in an efficient manner using latent strategies, and that's pretty nice. With that, you're able to capture non-stationarities, we can coordinate and influence, and we are using latent representations. But the thing that we don't actually get is this idea of getting data from humans and being able to train this reinforcement learning agent with data that is directly coming from humans. And I think it would be useful to be able to learn something from interactions with humans and try to merge that a little bit more. So in the second part of the talk, what I'd like to do is I'd like to just focus on that. I would like to think about how we can learn from interactions with humans and why that is useful or why that is feasible in settings. And for that, I'm going to simplify everything else. So for the second part, I'm not going to worry about non-stationarity. I'm not even going to worry about what the robot does, like if it coordinates or influences. I'm not even using my latent representation. What I'm going to focus on is just trying to learn from humans and see where we can get from there. And the idea that we are looking at here is, can we learn reward functions, human preference reward functions, so a robot can do the task the way that the human wants it? How can we bring in human data there and efficiently do that? And our key insight here is really the fact that most prior work that tries to learn from humans, like, usually assumes that we have access to some sort of experts' data, and that is like the only way to go about it. But I'd like to argue that humans are kind of like leaky pipes. They leak information like from all sorts of different sources. It's not just expert demonstrations. And looking at just expert demonstrations is only like one source, and it doesn't allow us to think about all these different types of avenues and sources and streams of data that are coming from humans. So what do I mean by that? Imagine we have a robot that, let's say, wants to pick up an object. And one way of doing that is by basically collecting expert demonstrations from a person, and based on those expert demonstrations, go ahead and pick up the object, right? Like, that is one way of doing that. That's called imitation learning. It's a very popular area. We saw CoRL papers going up in that area this year. It's been around for 20 years. And basically, the common paradigm there is, let's collect a bunch of expert demonstrations. Let's learn a policy or a reward function that captures and imitates expert demonstrations as closely as possible. But you're not really limited to just that, right? There is quite a bit of number of suboptimal demonstrations and observations out there. There are YouTube videos of people like cooking. And if I could use that, if I could actually use that, that would be wonderful. Or, for example, there are other sources of data, other modalities of data. For example, like, there's language instructions and narrations that has a lot of information in it. And if you could use that along with some of these other types of data, that would be awesome. Or other types of data are things along the lines of pairwise comparisons and rankings, right? Like, if you think about demonstrations, providing demonstrations on these robots with high degrees of freedom is usually pretty challenging. But if you can get the robot show you a bunch of trajectories and just ask you, well, which one do you prefer, or what ranking are you giving? Like, from that, I should be able to better learn like what the reward function is in a more practical manner. And finally, I want to emphasize that this robot is an embodied agent, right? It's different than an AI agent. It's different than just like usual ML, right? I can actually move this object. And given that I can actually move this object and provide physical corrections on this object, could I learn from those physical corrections? So these are areas that, in general, my group is pretty interested in, and we're doing work in all of them. But today, what I would want to do is I would want to just focus on two categories of things. So thinking about learning from pairwise comparisons and how we can do that actively and efficiently. And then I want to briefly talk about some of our recent work around learning physical corrections at the end. Okay, let's get into it. So what do I mean by pairwise comparisons? So what I mean by that is I can show two different trajectories to a user. I can show A and B, and then ask a user, well, which one do you prefer? And based on the human response to this binary question, I'm going to get some information about the underlying reward function that exists here. And for the moment, let's assume that this reward function is a linear combination of a set of features. So let's assume that there are some set of hand-coded features coming by a designer, and then this reward function is just some theta parameters. These thetas are weights for each one of these features, like, added up together. And the thing I'm trying to learn here are really the thetas. These are the weights, the parameters of my reward function. So imagine theta lies in a three-dimensional space. Then every question, every query that I'm asking from the user generates a separating hyperplane in this space. And then the human's response is going to basically tell us which side of the hyperplane is preferred. And based on that binary question, I'm going to get a better estimate of where the true theta, true parameters, really lie in this space. So then that's one question. But then the interesting research question here is, what is the sequence of most informative, diverse questions that I can ask a user in order to better learn what the reward function is in an effective and efficient manner? And we formulate this problem as an active learning problem. So our goal here is to actively synthesize queries and questions where we query the person and learn the reward function. So what does that mean? What that means is I'm going to come up with scenarios, fees here, fees correspond to those scenarios, separating hyperplanes, that try to maximize the information that I would receive from that particular query. And the objective here could actually be any information theoretic metric. We have tried entropy, we have tried determinantal point processes. In this case, I'm showing volume removal. So this is basically the volume that would be removed from the hypothesis space based on that question that you're asking. And that basically captures the fact that you are trying to optimize for asking a question that's the most informative thing in the world right now in my hypothesis space. And then we also have a set of other constraints here. We want to make sure that these queries that we are generating satisfy things like dynamics. So that is what the constraint is adding. So it makes sure that the scenarios are actually feasible and can run on the robot. And in addition to all of these, we assume that humans are also noisy to some level. So we incorporate a noise model of the human. So we don't fully trust the person if the person tells me I like A over B. But once we have this formulation, the idea is that every time step, I can run this optimization. Based on running this optimization, I can generate my next query, get the answer, and then go from there. And what that gets me is an effective and efficient way of learning reward functions. I'm showing this in a simple scenario here. So this is a simple 2D driving simulator where we have this autonomous car, which is the orange car. And after 0 queries where it doesn't really know what to do, after 30 queries, the car learns how to keep heading. And then finally, after 70 queries, the car learns how to keep heading and do collision avoidance and so on, which is kind of nice because, again, there was no expert demonstrations here. This is just based on 70 simple binary questions. And from 70 simple binary questions, we were able to learn like how to drive in this simple simulator. And that kind of shows the power of all these other sources of data that I really think we should tap into. So going back to this picture, I've been basically talking about the fact that, well, there's this underlying reward function. Let's try to capture what that is. And so far, I've been assuming this reward function is a linear combination of a set of features. And then that's pretty difficult, and that's not always the case, right? If you consider a robotics case, a lot of robotics cases are not like of the form of a reward, don't have reward functions of the form of a linear combination of a set of features. Let me show you an example here. So imagine that we have a robot that wants to play a version of mini golf. So this robot wants to push this ball here to any of these targets down the table. And it wants to do that through preference-based learning. So what it wants to do is it wants to show us trajectories, like 2 different trajectories, and then ask a human user, well, which one do you prefer? And based on that sequence of queries, it wants to figure out what the reward function should be. So if I assume my reward function is a linear combination of set of features, I should figure out what those features are. And writing out features in general is pretty difficult. If you look at other robotics papers that try to do the same thing, they usually have like text like this in their papers. They have, well, let's pick a feature that is an exponential of minus C4 times D4. And I'm going to pick C4 to be equal to 3. And you might be wondering, well, where does 3 come from? Or like, is that like magic? Like, where does this number come from? Or you might have more complicated features, like exponential of some distance in D2 and D3. And then we'll pick C2 to be 7 and C3 to be 3. Okay? So these numbers are not magic. They're coming from a lot of hyperparameter tuning. And basically that tells us that coming up with features can be incredibly difficult for some of these tasks. So what can we do? Can we do better? You might say, well, this is an old problem, right? Like feature generation is a thing that we could do. We could come up, like we could use deep learning, right? That's the whole point of using deep learning, so we don't write out these features. But the thing is, the moment you go there, then bringing the humans in the loop is also going to be really challenging, right? So if you use just classical like deep learning methods, then you should like think a lot harder to think about how you can learn from humans and how you can learn from these interactions with the humans. I want to mention one other point here. So if I don't want to worry about that feature design, and if I just want to pick like the simplest features in the world, like shot speed and shot angle, One other issue that could come up here is that I'm not even able to capture everything with a linear reward. If I use a linear reward, that linear reward with these simple features is always going to just capture the corners, and I'm not going to be able to get any of these other targets, because maximizing this reward always get these types of corners and boundaries, and not any of these other targets. So ideally, what I would want to do is I would want to use simple features here, and then be able to have a nonlinear function on top of them that allows me to pick any of these targets that are as main target, any of these targets as possible targets. And the way we do that is by using Gaussian processes, actually. So what we do is we do active preference-based learning over Gaussian processes, and using these simple features that actually allows me to target any of these goals down the line. I'm skipping the math detail here. This is an RSS paper. If you're interested in reading more about it, you can take a look at the details. And it's not easy to do active preference-based learning over Gaussian processes. So there are some math details that goes in it. But let me just show you how this works in practice. So if you look at the learned policies, if you use that linear reward, it's always going to target the boundaries. We're not able to even learn this task based on linear reward. But if you use a Gaussian process reward and do active preference-based learning over Gaussian processes, we are going to be able to target any of these goals based on the human preferences, which is kind of nice. All right, so let me go back to this diagram, right? I've been talking about pairwise comparisons and the fact that we can learn from that. And now I want to basically talk about physical corrections as another source of data, as another useful source of data in order to learn reward functions. So it turns out that if you have robots and they have bodies, you can actually move them around, and the robot can try to learn from that. And the thing is, if you have a robot that is trying to help you, let's say, unpack groceries, the human can provide a sequence of corrections on top of it. It's usually pretty difficult to correct the robot with one single correction. And that sequence of corrections are usually interdependent, and they kind of build on top of each other. And an idea that we have been thinking about here is, could we learn from a sequence of physical corrections by actually considering the interdependencies between these different corrections? Let me explain this over an example. So again, imagine that you have this robot that wants to unpack groceries, and the two robots are helping you here, and they're trying to put the bag on the blue region. That's where the robot thinks the bag should go. And there's this human, and the human has different preferences here. The human really wants the robot to put the bag on the green region. Maybe the human knows something that the robot doesn't know. Maybe the blue region is wet. Also, the human has a bunch of other objectives here. It doesn't want to stretch the bag too much because that breaks the bag. At the same time, it doesn't want to squeeze it too much because there's food in it. And it doesn't want to hit the obstacles like the Stanford hat or cabinets around, and so on. And the idea is that the robot is going to start off following this black trajectory, thinking that, well, I can go and place this bag on the blue region. That's where I'm going. And then the idea is that if you have a human here with these two robots, each one of them 7 degrees of freedom, the human is not going to be able to correct everything and satisfy all the priorities at the same time. Instead, the human is going to give these corrections by pushing the robot and a sequence of them to get the robot to do the same thing. And based on each one of these corrections, you're going to get a propagated trajectory based on the robot's belief of what the reward function is. And it can update that belief in an online fashion based on that sequence of queries that it is getting. And again, I want to emphasize that each one of these corrections, one at a time, is not going to capture everything. Even the last trajectory was hitting the Stanford hat. And then it's the sequence together that captures all the information about the reward function of the human. So how are we doing this? So the way we do this is, at the end of the day, I want to have a better estimate of theta, which is the parameters of my reward function. And if I think about probability of theta given corrections, well, I can write out Bayes' rule, and I have this posterior, which is probability of the corrections given theta. And these corrections are interdependent. So let's say I have k corrections, so psi1 through psi k. And the question is, how can I find this posterior? So here we are making this assumption that probability of these corrections that are given by the human, the sequence of corrections that are given by humans, is proportional to exponential of some sort of objective, some sort of reward function, which is a common assumption made when we are thinking about how humans act and give us corrections in this world. And the question is, well, what is that D? The way we are formulating that D is to have this trade-off between reward of each one of these trajectories discounted over time as well as the human effort, right? Like the human doesn't want to push too much or provide too much force here. So that combination together is creating this objective, this D function. And at the end of the day, that helps us figure out what this posterior is. Computing this posterior is not particularly easy. Like again, like computing the partition function here is going to give us a lot of troubles because of these dependencies between the trajectories. And we're making a set of approximations, like Laplace approximations and mixed integer programming to make this actually work. But at the end of the day, we have the posterior and we can have a better estimate of theta. Okay, so let me show this in practice. So here I have this person basically teleoperating, basically moving the robot arm and providing this feedback. And I'm comparing my algorithm, which learns from the sequence models, with an independent baseline where we're independently thinking about each one of these corrections. And here the darker colors correspond to the true preferences. And using our algorithm, we have a higher belief of the true preferences as opposed to this independent baseline. All right, so I've been basically talking about this idea of learning from humans and trying to bring humans in the learning loop. And the reason that I think that is useful is, and there's a way of doing that, is that humans leak information everywhere. Maybe we should try to use that information, all sorts of data that you're getting from humans, in order to better learn what they want and actually bring them to the robot learning loop. So now that we have that, for this last part, what I'd like to talk about is this idea of still learning from humans, but bring this similar ideas of latent representations to help us coordinate better and have the robot do the task in a more efficient way. And for that, I'm going to focus on a specific application. I'm going to focus on the application of assistive teleoperation. So if you think about these wheelchairs with robot arms on top of them, there are actually more than 1 million American users actually use them for various types of assistive tasks, like getting out of the bed or feeding themselves. And it's incredibly difficult to use them. So here is this person using a Jayco arm to try to do various types of tasks in homes. And here the person is basically using the joystick and controlling 6 things at a time, like X, Y, Z, and yaw pitch rule of the end effector. And that makes it really unintuitive and difficult to use, and you have to do all these mode switching type things to do anything at home. So an idea that we've been thinking about is that, well, if you think about these assistive robots, they're dexterous, sure, this dexterity makes them useful, but it also makes them hard to control. So the question is, can we find a low-dimensional representation here that makes controlling these robots more intuitive and easier? And you might be asking, well, Dorsa, why do you think such a thing even exists, right? It doesn't necessarily exist if you want to go from any point in the state space to any other point in the state space, right? Like for that, you do need all those degrees of freedom. There's a reason they exist. But the thing is, conditioned on a task, if you know you're doing a specific task, conditioned on the context, you might be able to learn a low-dimensional representation. So let me give you an example. Imagine I have a high-dimensional robot arm, and I know this robot arm is moving on a sine wave. One way of controlling that is to control all those degrees of freedom, but another way of controlling that to have a 1 degree freedom controller that just says +1 goes to the right and -1 goes to the right and to the left, and that is enough. So conditioned on me knowing that this is a sine wave, I should be able to do this task. All right, so how do we do this? So basically using that insight, we are collecting expert demonstrations from a caregiver or an expert, which is basically state actions and beliefs. And from that, you're encoding that data into a latent action representation, so Z1 and Z2. And the idea is, again, conditioned on the context, which is the states and beliefs here, we are able to train a decoder that reconstructs the same actions. And when we're training this autoencoder to get these action representations, we need to ensure that the loss function captures things like reachability or controllability, temporal consistency, and things of those form. And at the end of the day, you're getting like a 2 degree freedom controller that just does the task. Let me show you how this works in practice. So here I'm comparing end effector control, where we have 6 degrees of freedom, and latent actions, where we have these 2 degrees of freedom. And again, latent actions is much smoother and easier to use. You can easily move between the shelves for this long horizon task of making an apple pie, which is kind of nice and faster and more intuitive for the user. And on the left, you can see that the user is just having a hard time getting outside of like these modes, these linear modes and angular modes. All right, so latent actions, they're intuitive and they help us basically have these low dimensional controllers. But the question that we've been thinking about since then is this enough for precise manipulation? And we have done some work along these lines of making this a little bit easier, but because I don't have that much time, I'm gonna quickly just leave you with one thought that I'm really excited about, and we're actively working on it, which is basically this idea of trying to improve teleoperation here using shared autonomy and enable people to use these robots to feed themselves. I think assistive feeding is an incredibly exciting problem and difficult. It's a difficult robotics problem because you're picking up like food items that are deformable and they change over time even. And then it's a difficult human-robot interaction problem because a fork with a food is coming to your face and you need to make sure that it is safe and it is comfortable. And even if it is scraping the food inside of your mouth, it is doing it with the right forces in a way that is safe and so on. So we're collaborating with people at UW to better understand this problem. It's a difficult problem to also do during COVID times. So with that, I've been basically talking about this idea of learning intuitive controllers using latent representations. And that basically brings us to the fact that we can learn from humans. We can use these latent representations to make it easier to better coordinate. But the thing that I kind of skipped and I want to go back to and end the talk with is this idea of non-stationarity. I kind of like skipped that at the end, like for these two vignettes of learning reward functions and assistive teleoperation. But I do think that this is incredibly important, like the fact that people change and they're non-stationary. And we often tend to not worry about it as much because we are all about making an autonomous system, an assistive system, or an autonomous car that just does the task right? And we often don't really think about long-term interactions. The fact that when you put that system in a person's life, over time, that person is also learning, that person is also changing. And we should be able to capture that. This is a problem in assistive robotics. This is a problem in using these exoskeletons in rehab because the robot doesn't model the human. And one of the biggest problems there is over assistance, where it just does all the job because it doesn't capture the fact that the human is learning. This is a problem in driving. Like imagine that example I was talking about when the car cuts in front of you. That is going to work in that one particular step interaction. But that can make this car really angry, this black car, and it might come around and get ahead of you. And we should capture the fact that we are influencing people and those influencing behaviors can affect people's policies, people's reward functions, and they're non-stationary. And I want to emphasize this is incredibly important because as you're putting in more systems, more autonomous systems, autonomous cars on the road, it's not again a single autonomous car and worrying about the perception and planning of that single autonomous car. It is really about that interaction of that autonomous car with a whole group of people and how that changes the full dynamics of driving and what sort of conventions do we get when we think about repeated interactions. So with that, I think we should think about all these challenges: non-stationarity, coordination, and influencing. And I think latent representations provide a perspective on achieving this idea of collaborations and interactions more effectively. And I think we should try to learn from humans and bring that in the learning loop. With that, I'd like to thank the group during COVID time, and then thank you guys, and I can take any questions.
Thank you very much, Dorsa, for that inspiring talk. There are, let's see, there's a couple of questions. Maybe I'll just moderate. We have about a minute, so maybe we can ask 2 questions. The first question is about features. So the first question asks, if you use features extracted from data using unsupervised learning, do you see value in combining them with Gaussian processes rather than deep learning?
That is interesting. Yeah. So the Gaussian process there was basically bringing down the space that we are doing active learning over. So if we have like a deep neural network, like there's still like big questions there of how are we going to combine ideas around active learning there and how we're going to be smarter about the data that we collect. I think that could be combined with Gaussian processes, and that could be a good way of going about learning reward functions and even like doing things like safe learning, which is more plausible, like more easier to do with Gaussian processes as opposed to deep neural networks.
Okay, maybe I'll fit one more question in before the deadline. The next question is, do you think that we can scale to learning from different humans with different preferences simultaneously?
Yeah, that's a very good question. That's something that we're actually looking at actively right now. So yeah, so if you have data from multiple humans, then you have like a population data, and that could be a mixture model. So the question there becomes, how can you learn from mixture model, like from settings where you have this mixture models, and how could you do active learning in that setting? Like how could you actively generate queries from and be able to differentiate between these different humans when you have, let's say, a mixture of Gaussians or a mixture of different types of reward functions. It is actually a difficult problem, both theoretically and also practically. It's also not clear if active learning particularly helps in that setting or not.
Mm-hmm. Thank you, Dorsa. We have a couple more questions, but I think we'll leave them to type some answers and we'll move on to the next session. And thank you very much for that great talk.
Thank you so much.
Okay, so we're going to move on to the first session today. And this session will be chaired by Pulkit Agrawal. Hi, Pulkit.
Hi, Claire.
And you can take over now, Pulkit, in terms of introducing the speakers.
Well, thank you. So let's get started with session 3, general topics. And the first paper we are going to have is learning latent representations to influence multi-agent interaction. So this is what Dorsa briefly talked about, and Annie Z will be presenting this paper. Annie, you can share your presentation.
All right, let me share my screen. Okay. Can you all see my slides? Okay.
Yeah, everything is visible.
Hi, I'm Annie, and our new work studies multi-agent interactions between robots and other non-stationary agents such as humans. So before I talk about robots, let's first think about how people interact with each other. Specifically in this hockey example, the player on the left here is currently aiming from the right side of the goal. But the next time he approaches the goal again, he might pick a different strategy. For example, he might aim from the left side instead. And of course, this makes the goalie's job really difficult because this means that he has to deal with the different strategies of the opposing team during each offensive play. And so now similarly, when robots interact with humans or other robots, these other agents are non-stationary. They update their behavior in response to the robot. And so prior work for handling these multi-agent interactions would explicitly model the low-level policy of the other agent. But people can interact with each other with little to no effort. And they do this by keeping a high-level representation of the other person. And so we recognize that much like in human-human interaction, robots can also capture other agents with these high-level representations that change over time, which we refer to as their latent strategy. For example, consider these two robots playing air hockey. The ego agent on the left is a reinforcement learning robot that's tasked with blocking the incoming shots, while the other agent on the right is a rule-based robot that dynamically changes its strategy. And so the ego agent only observes the Y position of the puck as well as its own position. And to construct a non-stationary problem setting, the X position of the puck isn't provided to the ego agent, and instead has to be inferred from its earlier interactions. And so the ego agent can move its paddle up and down the X-axis, while the other agent has different strategies which correspond to aiming in different directions. Each trial lasts for a fixed number of time steps, and we define an interaction to be the resulting sequence of states, actions, and rewards of the agent. After each trial, the other agent will then select a new strategy based on the previous interaction. And importantly, the ego agent never observes the strategies or the actions of the other agent. So because naive reinforcement learning algorithms assume that the environment is stationary, they don't actually model the changing environment. And so when faced with a non-stationary agent, such as this one, the RL agent will learn to just pick one mode to block, and here it blocks on its left side. So for the robot to be able to adapt to the other agent, it first needs to model how its behavior is changing. While prior work focused on estimating the policy of the other agent and how that changes. Our approach instead learns a high-level representation of the other agent, which can change over time. To learn this representation from data, we train an encoder that takes in the previous interaction and predicts the next interaction's latent strategy. Then from this representation, the decoder reconstructs the rewards and transitions of the next interaction. And the whole point of this latent representation, Z, is to capture what the other agent will do next. So we train this encoder-decoder model to maximize the log likelihood of the rewards and the transitions that we're seeing across all of the interactions. And so having learned a model of the other agent, we can now train a policy that's conditioned on the predicted latent strategy. This policy will give us different behaviors for different predictions. And so it basically gives the ego agent the ability to react to the other agent. Now to recap, during training, our approach first trains an encoder-decoder model to learn a representation of the other agent. Then we train a policy conditioned on this representation so that the agent can react to the other agent. Now putting all this together, during a new interaction, the encoder predicts the other agent's latent strategy. The ego agent then carries out the policy conditioned on this prediction, and this process repeats. So we call this whole framework learning and influencing latent intent, or LILI. We first considered a simple navigation task here with the ego agent represented by teal and the other agent represented by gray. The ego agent always starts each interaction at T1, while the other agent sits somewhere along the shaded blue circle. And during each interaction, the ego agent needs to capture the other agent as quickly as possible, but it never observes the position of the other agent and only receives reward based on how far they are from each other. The other agent is only allowed to move between interactions, and specifically it moves either clockwise or counterclockwise, depending on whether the ego agent's final position is inside or outside of the circle. Here we visualize the trajectories taken by the ego agent in teal, where the teal circle represents the final position of the agent, and each frame corresponds to a single interaction. So this first policy is trained with soft actor critic, which is a standard reinforcement learning algorithm that doesn't model the other agent. And this policy at convergence moves to the center of the circle in every interaction. And that's because without knowledge of or any mechanism to infer where the other agent is, the center of the circle is where the agent receives the highest reward. In contrast, our method LILI successfully models the other agent's behavior and can capture the other agent in each interaction. But notice that the other agent is captured along this lower part of the circle. If the goal is to reach the other agent as quickly as possible, then ideally the other agent should be positioned at the top of the circle, where the ego agent is closest. So in other words, the ego agent should influence the other agent to move towards that blue region. So instead of simply reacting to the other agent, what we actually want is to learn a policy that can influence its strategy. This influential behavior can be learned by maximizing the long-term rewards across interactions. And this objective naturally motivates the ego agent to act in a way that leads to more desirable future strategies in the other agent. And so now returning to the navigation example, as expected, we see that the LILI agent with influence learns to trap the other agent at that top of the circle. This is where the target is the closest to the ego agent and where it receives the highest rewards. And we see that again here in this plot of the rewards collected during each interaction. LILI with influence almost matches Oracle performance, while LILI without influence earns slightly lower rewards. In this next task simulated in Carla during each interaction, the ego agent, which is controlling the blue car, needs to pass the other agent, which is controlling the tan car. The other agent recognizes that the lane the ego agent passes in is faster, and so it'll merge into this lane during the next interaction. The converged soft actor critic agent changes to the left lane in every interaction, even when the other agent moves to the left lane too. And this results in near collisions. On the other hand, LILI correctly anticipates the lane that the other agent will switch to and it'll switch to the opposite lane accordingly. And because the strategies in this setting are equally rewarding to the ego agent, here Lily without influence results in the same performance as Lily with influence. Finally, we tested our approach in the air hockey game described earlier. So as a reminder, the other agent strikes the puck either to the left, down the middle, or to the right. And after each trial, the other agent will select a new strategy based on the last interaction. Specifically, it always aims away from where the ego agent last blocked. So the ego agent earns +1 reward for blocking the puck. And now let's pretend the robot has an easier time blocking on its left side for some reason. And so it earns +2 reward for blocking shots that come down the left side. And this means that influencing the opponent to aim to the left side more often will lead to higher long-term rewards. So we first trained a policy with soft Dr. Critic. And again, because it doesn't model the opponent, this agent learns to block only one mode, which is its right side. And near the end of training, it switches to blocking left instead every time, which earns it higher rewards. And here, instead of rewards, we plot the success rate over training, and we see that the final policy achieves about a 40% success rate. However, we see that Lily can block a lot more successfully than soft Dr. Critic, but it doesn't always get that bonus reward for blocking left. And that's because it's not explicitly trained to influence the other agent's strategy. Lily blocks successfully about 90% of the time. And finally, we look at Lily with influence. So this agent, as we can see, can manipulate the other agent to alternate between left and middle shots. And by doing this, it achieves higher overall rewards. So looking at success rate only, we can see that Lily with influence has a similar success rate as Lily without influence. But where we actually see a difference is when we look at how frequently the opponent fires left, middle, and right. Lily with influence leads its opponent to fire left the most often, 41% of the time, while without influence, the distribution over the strategies is uniform. So we tested the policies learned by a soft Dr. Critic and Lily against a human expert. So this human expert follows the same set of strategies as the robot opponent, but here the human has imperfect aim. The soft Dr. Critic agent success rate is 45%, while Lily's is 73%. So to conclude, we can often capture the behavior of non-stationary agents with these high-level representations. And with these representations, the agent can learn to anticipate and influence other agents across repeated interaction. Thank you.
Thanks, Annie. Good talk. So I have a question for you. So the question is, when talking about multi-agent setting, are we focusing on collaborative scenario or a competitive scenario or an interaction scenario?
Yeah, so this framework isn't specific to collaborative or competitive scenarios. We're looking at any setting where there are two agents interacting with one another. And the nature of the interaction basically has to be encoded in the reward function. So for example, in the point mass navigation task, the ego agent is rewarded to capture the other agent. And so in that sense, you can view it as perhaps a competitive scenario.
Okay. So if there are no other questions, I will ask one question. So in the scenario that you are modeling long-term interactions, did the variance of your reinforcement learning updates increase because of the increased time horizon? And if so, then how did you model it?
Yeah, it actually did. So for example, in the point mass navigation task, oftentimes, especially in the middle of training, when it was still trying to capture the other agent to that top of the circle, it would sometimes lose track of the other agent. And that's where the rewards would drop again. And essentially one thing that we did try was instead of we essentially, instead of treating it as one long sequence, all the interactions as one long sequence, we would segment them so that we had, I guess, shorter sequences of interactions.
Okay.
And that still led to that influential behavior, which was nice.
So we have a couple of more questions, but I don't think we'll have time to cover them. But let's thank Annie for her talk, and feel free to get hold of Annie to get your questions answered. And now we will move on to the next speaker. So our next talk is on flexible skill formation with learning from demonstration and reinforcement learning via representation sharing. And Meet will be presenting this talk. So Meet, take it away.
Thank you, Professor Agrawal. I hope you can see my slides. Okay. Hello again. I am Tulan Akbulut, a master's student from Boğaziçi University, Istanbul, Turkey. I'm supervised by Erhan Öztop and Emre Uğur. It's my pleasure to present our work here. We shared the code and data of this work on our project page. Learning from demonstration is a widely used method to teach robots dexterous skill. However, the performance of the robots depends on the demonstration distribution. Let's assume that 6 demonstrations are given to an LFD model. After training with these demonstrations, when the model is requested with the black dot to perform the skill within the demonstration range, it can generate the required black trajectory. However, if the required trajectory should follow a path outside the demonstration range, task requirements may not be satisfied and further adaptation is required. In this work, we study following challenges in adaptation during task extrapolation through trial and error and skill transfer. The relations between task parameters and trajectories are often highly nonlinear and complex in real-world problems. Therefore, excessive policy updates may be required for adaptation. However, experiments with real robots takes time and resources. Another challenge is preserving demonstrated behaviors automatically during adaptation, because it can be more practical than to encode these behaviors in a reward function. These behaviors can be related to safety, robot and environment constraints, or other user preferences. Skill transfer becomes extremely difficult when it happens between robots with different embodiments. In this case, additional engineering efforts are required to find correspondences between policies. In literature, state-based correspondences are sought to transfer the policy, but this approach requires state pairing beforehand. We propose adaptive conditional neural movement primitives called SCNMP to address these challenges. We use conditional neural movement primitives as the base LFD model to learn skill representations, because this state-of-the-art model can learn nonlinear relations between trajectories and task parameters using only a few demonstrations. Let's have a look at how representations are found. This framework consists of one encoder and one query network. Random number of observations from sensor motor trajectories are passed through the encoder network to get corresponding representations. Then these representations are merged to find the trajectory representation. Using this representation, the query network produces parameters of a Gaussian for queried time steps. It's also possible to condition this Gaussian distribution with external task parameters. So at test time, the model generates the trajectories by querying all time points for given task parameters and observations. Finding trajectory representation from random observations and trajectory generation with respect to task parameters are two important features we exploit in our framework. In order to achieve the goal with given task parameters, CNMP model is conditioned with these parameters to generate the required trajectory. Then the generated trajectory is given to robot execution. If the robot does not achieve the task, reinforcement learning agent is triggered. The RL agent is initialized with the same LFD model. And this network updates its internal parameters via reinforcement learning, which is alternated with error-based supervised learning. For observation and task parameters coming from the demonstration set, supervised learning loss is used. When the inputs are coming from extrapolation cases, the same network is updating by the policy gradient loss. In practice, this allows the system to generate novel trajectories that are encoded into the same latent space with demonstrations and share similar characteristics with them. After the RL agent finds the satisfying trajectory for the new task, this new trajectory is fed back to the LFT system as a new demonstration. Afterwards, the loop continues, our framework improves itself at each cycle and becomes less prone to failure. In skill transfer scenario, both robots have their own SNMPs and they form a common latent space during learning from demonstration. Here, an additional mean square error loss is defined to make corresponding representations similar. Our representation learning method can handle different number of joints and different number of observation points because it finds the representations at skill level. Therefore, no time warping or state pairing mechanisms are required. In this part, task parameters are not used, not to involve any biases about the task. At test time, skill transfer for a novel task can be achieved by transferring skill representation from the first robot to the query network of the second robot. Afterwards, the target agent can perfect the skill using its RL agent. We made 4 simulation and 2 real robot experiments. The first experiment is the working example where aim is to extrapolate to a novel wire point outside the demonstration range. LFT on the model cannot generate a trajectory that goes through the specified point. RL on the model generates a trajectory that maximizes the reward but does not preserve the demonstrated shape. The generated trajectory by SCNMP achieves the task while preserving the shape. In order to evaluate our model's adaptation capability to novel goal points while controlling a robot, we adapted this experiment from Stark et al. And compared SCNMP with their state-of-the-art post-adaptation method. 9 demonstrations of pushing the black obstacles to a goal point are provided to a 3-degree of freedom planar robot. Then the robot is requested to push the black obstacle to a novel goal point. Here, baseline uses one movement perimeter model for each goal position, whereas we can use a single model for all goal positions. On the left, demonstrations are shown. And on the right, you can see the performance of the pure LFT model and the performance after adaptation. As shown with the blue plot, our model finds the successful trajectory or requires small adaptation for all interpolation goal points. For the extrapolation goal point, SCNMP achieves the task around 60 iterations. As shown in the table, SCNMP requires order of magnitude fewer samples than the baseline to adapt. In this experiment, the aim is to evaluate our model's adaptation capability to novel environments. The experiment is adapted from Everton et al. For comparison with their state-of-the-art adaptation method. The aim is to produce a trajectory that starts from the fixed blue point, avoids the randomly positioned wall, and ends at the randomly selected red goal point. Demonstrations are given for 30 environments. Sample demonstrations are shown on the left. The performance of LFT on the model and SCNMP is shown together in the video. As shown in the graph, the baseline and our method are competitive in terms of the number of environments used. However, if we plot the same graph with respect to sample trajectories used, we see that SCNMP requires many fewer samples than the baseline for each environment. This table illustrates that SCNMP is order of magnitude more sample efficient than the baseline for a single environment and for the whole task. We implemented 2 experiments to test our model's performance with real robots. First task is obstacle avoidance task, where task parameters are object height and wall height. Here the challenge is learning nonlinear relationship between parameters and 6-degree of freedom complex trajectories to adapt novel heights. Second task is a marble pouring task, task parameters here are weight of container and desired pouring amount. Here the challenge is generating motion trajectories from weight-based rewards to pour a novel desired amount. The last experiment aims to evaluate the transfer learning capability of SCNMP. We adopted this experiment from Gupta et al., where two robots with different morphologies are provided with proxy skills to learn how to transfer policies. Given that 3 degree of freedom robot has the skill to achieve a button pressing task, 4 degree of freedom robot should benefit from its experience and acquire the skill quickly. Note that this task is extremely hard to learn from scratch because the robot does not receive any reward unless it can touch the button. 3 proxy tasks, reaching, pushing, and peg insertion, are used to form a common latent space. Pushing task is shown on the left. For the test task, a demonstration is provided to 3 degree of freedom robot, and 4 degree of freedom robot is expected to approximate the skill by skill transfer. For 12 demonstrations, how common latent space is formed is illustrated. Our model finds representations at skill level, 12 representation clusters for 12 skills, therefore does not require additional state pairing techniques. The effect of common representation and reinforcement learning is shown here. For the robot almost acquires the skill after transfer, and our RL method is used to perfect it. In conclusion, we propose adaptive conditional neural movement primitives that is order of magnitude more sample efficient than the state-of-the-art methods. It preserves demonstrator shape by training with demonstrations continuously, and it enables skill transfer between robots with different embodiments by finding a common latent space at skill level without explicit time warping and state pairing. Thank you for listening. I would like to answer your questions.
Thanks for your talk, Meet. So if people have questions, feel free to post them in the Q&A, and I'll be happy to read out those questions. In the meantime, so one question I have is, can you maybe highlight the key differences between ACNMP and, say, a variational autoencoder in learning the motion primitives?
Okay, I can do that. I want. Okay, here it is. The main difference from a traditional autoencoder is that here the input number is changing. The observations from this trajectory are coming from random points, and also its number is also random. These observations are passed through a parameter sharing encoder separately, and afterwards these representations are merged to find the trajectory representation. Therefore, it can increase its own data set by taking random permutations from these trajectories.
Okay, thanks. So I have a follow-up question from Jackie. Are there failure modes or disadvantages of using conditional neural processes versus other models?
In my experience, conditional neural primitives or this conditional neural primitive method can map task parameters to trajectories better than the other movement primitive methods. Therefore, I think our approach requires fewer samples than other methods.
So is there any disadvantage of using your approach as compared to other approaches?
Oh, okay. Is there any disadvantage? I think I can answer this one later because I'm not sure.
Okay, no worries. And one last question. So in the 3 degree of freedom and the 4 degree of freedom experiments that you showed, of the pushing task and the pressing the button task. So did you need any alignment when the pushing task was being done, or no alignment?
No, like the thing is that we don't need alignment, but like the time vector is normalized between 0 and 1, but like warping alignment, like dynamic time warping, is not required because, as I said, the latent space is formed at skill level. So like the observations are coming from random time points, etc. So for each skill, I obtain one representation. Therefore, I'm not worried about how they behave with respect to time.
Okay. Thanks a lot for your talk.
Thank you.
I encourage everyone to catch hold of the speaker if you have more questions. And now we will move on to the next presentation. And that is learning from suboptimal demonstrations via self-supervised reward regression. And that will be presented by Lotte. So Lotte, take it away.
Yeah, sure. Thank you, Professor Agrawal. Can you see my screen?
Yeah.
All right. Thank you. Okay. So, hello, everyone. My name is Letian Chen. Today, I will present our paper, Learning from Suboptimal Demonstration via Self-Supervised Reward Regression. This work is done in co-robotics lab with my co-author, Rohan and my advisor, Matthew Gambley. Researchers are developing robots for application in healthcare to manufacturing, scientific discovery, and even assistive household tasks. However, traditional design for task controllers requires an army of robotic experts for each task, greatly limiting the possibility of robots. In contrast, learning from demonstration techniques empower end users to program robots to achieve their personalized goals without robotic expertise. Humans are often able to give instinctive but suboptimal demonstrations that could be leveraged for robot learning from demonstration. This suboptimality is often due to diverse heuristics humans develop to compensate for cognitive limitations. However, LFD research often assumes access to optimal demonstrations and generally cannot do better than the demonstrations, even if they are suboptimal. Preference-based RL bypass the requirement of optimal demonstrations, but queries humans for preference, which is a cost-intensive process. In our paper, we produce a new state-of-the-art learning from suboptimal demonstration by first characterizing the relationship between a policy's performance and the amount of noise injected. We characterize the relationship via a low-pass filter. Our reward learning framework, SSR, then learn from this more accurate noise performance relationship. We further propose a more robust noisy trajectory synthesizer, noisy ARL, to handle covariate shift for both the policy and the reward of ARL. Lastly, we show SSRR achieves a higher accuracy in reward learning, and the trained policy achieves a higher performance than suboptimal demonstration and previous state-of-the-art DREX. We also demonstrate our algorithm in a robot table tennis topspin strike task as shown in the video. So first of all, why do we need noise injection? PPRL and T-Rex could learn from the suboptimal demonstration by explicitly asking humans for preference. DREX, however, avoids the requirement and automatically generates the ranked trajectories by injecting varying levels of noise eta. Injecting noise means transforming a policy pi to be eta greedy policy pi eta, which draws a random action with probability eta. DREX achieves automatic ranking by assuming that the higher the noise level is, the lower the trajectory should be ranked. Next, let me introduce what the noise performance relationship is. Here is an optimal policy trained by software actor critic on half cheetah. If we inject the noise into the policy, the performance will drop. And with more and more noise injected, the performance becomes worse and worse. But how does the performance degrade with varying noise levels? Is it a linear relationship, an exponential relationship, or a logarithmic relationship? The noise-free policy achieves a high ground truth reward of almost 9,000. The 0.3 noise policy achieves a reward of 3,000. And the last two achieves even lower reward. If we plot the corresponding noise performance data points, we could obtain a noise performance curve, which in this case is a decay-like relationship. This is what we call the noise performance relationship. Prior state-of-the-art DREX works by 4 stages. First, it employs behavioral cloning to obtain a policy from the demonstration state action pairs. Second, DREX inject varying levels of noise into the behavioral cloning policy to create noisy trajectories as we introduced. Third, DREX automatically generates ranked trajectories by noise level ranking. And finally, DREX learns a reward function from the ranking information by the loose shepherd rule. We argue DREX has 2 key drawbacks. The first one is behavioral cloning, which suffers from covariate shift when synthesizing noisy trajectories, which means the policy error compounds and the agent gradually enters a state space that never occurs in demonstrations. It will make the agent choose random actions and result in even more far away from the desired trajectory. The second one is unhelpful inductive bias from loose shepherd rule when learning from the binary rank information. For example, if we apply loose shepherd rule to the 3-level noise eta0, eta1, and eta2, and their corresponding trajectories tau0, tau1, and tau2, the resulting reward of tau1 will be the average of the reward of tau0 and tau2, which means a linear noise performance relationship. No matter what the noise levels are, what the environment is, and what the policy is. In our paper, we first characterize the noise performance relationship. To do it, we first train a policy with an RL algorithm and then inject noise and calculate the performance at each noise level, as we did for half cheetah. We can repeat the process for other environment and policies trained with other RL algorithms. As we could observe, the noise performance relationship is heterogeneous, which is contradictory to loose shepherd rule's assumption. If we apply loose shepherd rule blindly, it sometimes, in some situations, it might fit well, but in most cases, it won't fit the actual noise performance relationship. However, a sigmoid function could well capture the noise performance relationship and adjust to different environments, policies, and the noise levels. In our method, we utilize ARL to obtain an initial policy and an initial reward, which is a learned reward from the ARL discriminator. We then generate the noisy trajectories through interaction with the environment, and then criticize the noisy trajectories by the initial reward. Through this way, we could get a sense of how performance degrades with varying noise levels. We can then send through a low-pass filter to characterize the noise performance relationship. In our case, we utilize the sigmoid function as our experiment shows it could capture the noise performance relationship very well. We could then train a reward function by regression to the sigmoid function. Since ARL's initial reward R is biased to evaluate its policy, evaluating R on noisy trajectories may not be reliable because of covariate shift. Therefore, we propose noisy ARL, which injects noise in ARL's training so that ARL is more generalizable to the state space, and we employ importance sampling to adjust the discriminator loss due to the change of sampling process from policy pi to the noisy policy pi eta. The two steps in noisy ARL provides a more robust reward and policy learning, enhancing the ability to accurately characterize the noise performance relationship. We carry out our experiment comparing with the benchmark DREX by a 3x2 experiment design. The noisy trajectories could be generated via 3 different methods: behavioral cloning, ARL, or noisy ARL. And we apply either SSRR or our benchmark DREX to learn from the noisy trajectories. We computed the correlation between the learned reward function by SSRR or DREX with the ground truth reward shown in the table. SSRR learning with noisy ARL noisy dataset generation achieves the best correlation across the 6 combinations. We could observe DREX performance fluctuates a lot with different noisy dataset generation methods, further showing that the noise performance relationship is heterogeneous. And when the relationship fits loose chaperone assumption, it can work well, while when it doesn't fit well, DREX performs poorly. In contrast, our method adapts to different noise performance relationship via a flexible sigmoid function, achieving a relatively stable performance. We further show the correlation plot of SSRR and DREX performance on half cheetah. The red dot represents the original demonstration. The blue dots represent the datasets in the noisy dataset, which is the training data for SSRR and DREX. The green dots are unseen test data. We could observe that SSRR preserves the reward structure far beyond the demonstration point, while DREX twists the reward structure. We further utilize the software actor critic to optimize policy on the learned reward function and show that SSRR's policy outperforms the suboptimal demonstration and the DREX. We further demonstrate our method in the robot table tennis setup. The task we wish to accomplish is a top spin strike. In demonstration, humans give suboptimal demonstration with lower speed and spin, which are represented by return lateral speed and vertical acceleration respectively. ARL could replicate the demonstration with a little lower lateral speed, but is unable to achieve a better performance than the demonstration. SSRR, however, performs significantly higher speed and spin than both the suboptimal demonstration and the ARL policy. In conclusion, we developed self-supervised reward regression, a framework to learn from suboptimal demonstrations. We illustrate its superior performance through its capability to learn a more accurate noise performance relationship and a more robust noisy data synthesizer. Thank you. I would love to answer any questions.
Thanks, Lotte. So if anyone has questions, feel free to type in the Q&A box. In the meantime, one question I have is there any intuition that you have why the sigmoid function works better than the loose shepherd? And are there any failure cases that you know where the sigmoid function does not matches the noise statistics?
Yes, that's a good question. So the reason why we choose the sigmoid function is that we first plot the noise performance relationship for several different policies and environments, and observes that it could well capture the sigmoid function will capture the trend, and while the loose chaperone is constant for all the different environments and policies. For your second question, what's the failure case where sigmoid function could not capture the result, could not capture the noise performance relationship well, is here I give 2 possible counter examples. So first one could be tasks that with a little noise injected, the performance will drop abruptly so that it doesn't conform to a sigmoid function. Another counterexample is when you give a total failure demonstration, like a super suboptimal demonstration, such that like adding noise will not degrade the performance further. Then the noise performance relationship will just be a flat line, and like SSRR cannot do better than demonstration in this case either.
Okay, thanks, Lotte. And if there are no more questions, we will move on to the next talk. Let's thank the speaker once more. And the next talk is domain invariant robot learning for sim-to-real transfer. And the presenter is Ajit Tanut. Ajay, you can take it away.
Thanks, Pulkit. Yeah. Hey guys, I'm Ajit Tanwani. I'm postdoc at UC Berkeley. In this work, I'll be presenting a domain invariant robot learning approach to adapt deep models to new environments where the testing data is drawn from a different distribution as that of the training data, such as in transferring models from simulation to the physical world. Collecting and labeling large-scale training data in physical environments is time-consuming and cumbersome. Generating this data in simulation provides a feasible alternative, as it is also evident by a number of papers that were presented at CoRL this year. But the caveat remains that the modeling inaccuracies do not generalize to the physical world. In this work, we investigate how we can mitigate these discrepancies across domains, in particular across image and object distributions for downstream tasks such as vision-based decluttering. In contrast to widely used domain randomization approaches that naively treat the discrepancy between the domains as variability in the simulation parameters, we focus on sample-efficient feature-based domain adaptation methods to learn invariant feature representations for transferring to a new environment. More formally, we analyze the situation with two domains, one corresponding to the simulator or the source domain, and the other corresponding to the real or target domain. The simulator domain has lots of labeled examples, while the real or target domain has very few labeled examples, but can have a lot of unlabeled examples. And we seek to learn a policy such that the empirical error on the target domain is minimized. And the policy here is represented by a concatenation of the functions f and g. Since the two domains are different, there's a mismatch between the joint distributions of the source and the target domain. Commonly used domain adaptation approaches learn an invariant feature transformation by aligning the marginal distributions across domains, that is at the source and the target distribution. They implicitly assume that the conditional distributions of the transformed features also remains similar across domains as shown in this side of the figure. Aligning the marginal distributions only, however, can create ambiguity in class alignment that can result in a negative transfer to a new domain. To this end, we present a domain invariant representation learning approach that semantically aligns both the marginal and the conditional distributions by leveraging upon a few labeled examples of the target domain. The joint discrepancy across both the domains is minimized by minimizing the sum of the marginal discrepancy and the conditional discrepancy across domains. So the marginal discrepancy here refers to the distance between the probability distributions of the transform features in the shared feature space, whereas the conditional discrepancy refers to the resulting distance between the policy distributions at the output level. To make it concrete, let's consider this two-dimensional synthetic example with two classes as shown in orange and blue. Filled circles in this example represents the labeled examples, while the empty circles are unlabeled examples. In the conventional supervised learning scenario, we see that the decision boundary in black on the right plot fits well to the training data, but does not generalize well to the target data drawn from a different distribution. Aligning the marginal distributions in the shared feature space as represented by these overlapping density plots however, results in a cross-mapping of class categories with negative transfer. Intuitively speaking, the apples of a simulator are being aligned with the oranges of the real domain in this case. Even if there exists a label shift with an imbalanced class ratio in the target domain, such as that of 0.1 in this example, that is the ratio of class categories between the source and the target domain, we see that it leads to uneven mixing of class samples across the decision boundary, with the constraint being put that the marginal distribution should align in the shared feature space. Now, DERL addresses the cross-label mismatch and the label shift problem by aligning both the marginal and the conditional distributions with a few labeled examples in the target domain, as seen here with these overlapping contour plots, as well as the density plots in the shared feature space. So the main idea behind DERL is that we are using a few labeled examples as anchor points and drawing the respective unlabeled target distributions towards them to mitigate the conditional discrepancy across the domains. This main idea is grounded in theory as well. The most well-known result in domain adaptation is from Ben David et al. In 2010, which suggests that the target domain error of a policy is bounded by the sum of the source error, the marginal discrepancy across domains, and the error of the best performing model. That is the model that gives the lowest error jointly in both the source and the target domains. This best model error is conventionally assumed to be small in unsupervised domain adaptation approaches. More appropriately, this best model error term can in turn be formulated as the cross-domain performance error of the optimal policies, which is represented here by the cross-overlapping area between the class categories in the shared feature space. And this area would be non-zero for cross-label mismatch or the label shift examples that we presented, which in turn are representing the conditional discrepancy between these distributions. So the target error is therefore bounded by the marginal and the conditional discrepancy across domains that DERL seeks to optimize. The overall algorithm optimizes 3 additional loss functions on top of the policy loss. One is the marginal alignment loss, which is optimized with adversarial learning by using a domain discriminator to distinguish between source and target examples. The conditional alignment loss is also optimized with adversarial learning for each class separately by using a few labeled target examples and predicting pseudo labels for the unlabeled target examples if required. And third is the triplet distribution loss, which makes the conditional distributions disjoint in the shared feature space. In contrast to working on the individual examples, the triplet distribution loss operates on distributions of positives and anchors belonging to the same class, whereas the negative distributions are centered on examples belonging to a different class. Let's first benchmark the performance of DERL on digits datasets, that is MNIST, MNIST-M, SVHN, and USPS in these source to target configurations. We train the model on labeled source and unlabeled target data and evaluate the results on a held out target set. We compared the performance with reconstruction-based domain adaptation approaches, DAN, which aligns the marginal distribution across distributions, triplet loss, associative domain adaptation, and MCD, and a few shot and domain adaptation and DAN for semi-supervised scenario. The results suggest that MCD performs better among unsupervised approaches by minimizing the conditional distribution discrepancy across domains, but it suffers in problems with large domain strips such as USPS to SVHN or MNIST to SVHN. DERL consistently gives better performance across all these problem statements in comparison to the unsupervised and semi-supervised domain adaptation approaches in handling large domain shifts. TSNE visualization results suggest that DERL compactly represents the class distributions across data sets better in comparison to DAN that only aligns the marginal distributions and the no adaptation scenario. All right, let's now turn our heads back to investigate the feasibility of vision-based decluttering by sim-to-real transfer with the proposed approach. To do so, we generate about 20,000 simulation images using publicly available object meshes in the simulator that is split across 12 object categories. Similarly, we collect about 200 real images with the mobile Toyota HSR using commonly available household and machine shop objects that you see on your right. So the robot declutters the environment by first recognizing the objects on the floor and subsequently planning the grasp points to pick them up and deposit them in the target bins. So there are two networks involved here. The grasp planning network is learned on top of synthetic depth images using the simulator data only. The grass labels are obtained by evaluating the grass samples under robust wrench resistance metric, which is used to evaluate the grass success probability as used as the ground truth labels. And the object recognition network combines the data from the two domains using the DERL approach. We modify the base architecture of single-shot object detection network to add domain and class conditional domain classifiers on top of the feature pyramids. Results here indicate, results for the deep object recognition network here indicate that naive transfer of models from simulation to the real results in a poor performance with about 26% accuracy only. Naively combining sim and real data is also suboptimal, whereas triplet, DAN, and MCD improves the performance in transferring to the real environment. DERL mitigates both the marginal and the conditional discrepancy for more robust sim-to-real transfer. Experiments on Toyota HSR show that the robot is able to grasp a wide variety of objects with about 86.5% accuracy, in contrast to 76% with the PCA baseline grasping policy. The video here shows the real implementation with the Toyota HSR. We randomly drop a subset of real objects on the floor. The robot recognizes the objects, plans the grasp, and puts them in the target bin. The objects are allowed to overlap after they fall down on the floor. In case the objects overlap by more than a certain threshold, the robot executes a singulation primitive to isolate these objects, and subsequently plans across these primitives to declutter the floor in a repetitive manner. Right, in our ongoing work, we are extending DERL to handle conditional distributions mismatch in continuous spaces, such as in smoothing or folding tasks with cloths or fabric. We are interested in learning domain invariant models across multiple environments with a fleet of robots, and also to close the real to sim gap in learning generalized models across new domains. The main takeaway of this work is that domain randomization is a promising approach, but for sim-to-real transfer, but one should not stop there. Incorporating the real data by aligning the marginal distributions can lead to performance improvement, but may also result in negative transfer with cross-label mismatch or label shift that we highlighted in this study. We introduced DERL that semantically aligns both the marginal and the conditional distributions for provably efficient domain adaptation. And presented as use case for a real robotics application. So yeah, I'm happy to take further questions at this point.
Thanks a lot, Ajay.
Awesome.
So one question from Nimrod is a follow-up to what you were discussing about extending to continuous action spaces.
Yeah.
So, I mean, do you have any concrete suggestions on how to apply this method to regression instead of classification problems?
Yeah, we've been looking into this problem as well. I'll suggest you to drop in the extended session because the answer is slightly longer, but you can apply this discriminator at the domain level at the feature transformation level, but at the policy head, you can also use a similar state action discriminator, or even if there's the dynamic mismatch, you can use a state action next state discriminator as well. So instead of using K per class discriminators, you would have to rely on some form of instance reweighting here, which we are investigating at this point for extension as well. So you can use it, but it's a little bit different formulation, which I can probably present the block diagram in the extended session here.
Okay, I have one more question. So did you apply DRL just for object detection, or for grasping as well in the decluttering task?
Yeah, thanks for this question. So far in this study, we reported the results for the object detection or recognition part. We have investigated for the grasping problem as well. The results seemed more robust because the depth image proved sufficiently robust in transferring across the kind of examples that we saw. But in other examples, we see some promising aspects in applying it across depth images as well. So the results here were for the object recognition network only.
Okay. And one last question I have is, so you talked about in domains where there were no target labels, you generated fake labels. So can you say a bit more about that?
Yeah, that's a great question. So we applied this for a few domains. One was this 2D synthetic domain, the digits domain, and then the object recognition domain, and there's some other studies as well. So for most of them, we did not have to use the pseudo labels, but for instance, for the object recognition network, we had to use the pseudo labels after pre-training the source network and using them to further align the conditional distributions. So it's an interplay between aligning the conditional distributions, which requires more robust labels, in contrast to the marginal distributions alignment, which comes in a way for free because of the source and target domain labels. And this interplay is somewhat domain dependent. So you may have to tune this part in terms of how much pseudo labels are required in comparison to using just a few labeled examples that you can provide as an outset.
Okay. Well, thanks a lot. Yes, thanks a lot, Ajay. And again, I encourage everyone to get hold of Ajay in the extended sessions. And with that, we will close this session and I will hand it over to Claire.
Thank you, Pulkit. Thanks for chairing the session. And thanks again to Ajay and to Laishan, Mette, and Annie for their great talks. All right, so we're going into a break now for 13 minutes, and we're going to start again our next session at the top of the hour. So please stay tuned and rejoin us at the top of the hour.
Okay, great. Welcome back after the break. It's my pleasure to chair this next tutorial session, which will be given by Andreas Krause. Andreas is a professor of computer science at ETH Zurich, where he's heading the Learning and Adaptive Systems group. He also serves as the academic co-director of the Swiss Data Science Center and also is the chair of our recently founded new ETH AI Center. He received various awards. I'm just going to mention very few of them. He received the Deutscher Mustererkennungspreis, an NSF Career Award, the Okawa Foundation Research Grant, but also various Test of Times awards for his research, for example, the ICML Test of Time Award 2020. His research on learning and adaptive systems has had impact in various domains. I think in particular, his work in the area of Gaussian processes, submodularity, but also safe reinforcement learning. Now, the latter is exactly the topic of today's tutorial. It's an extremely timely topic, I think, as it addresses a central challenge for robot learning in the real world. So if you have questions during the tutorial, just post them. I'll be collecting them for Andreas. And so now, without further ado, I'd like to welcome Andreas, and we're very much looking forward to your tutorial.
Oh, thanks a lot for the kind words. Let me share my screen. Can you see my slides?
Yes.
I hope so. Okay, so thanks a lot, Melanie, for the kind introduction. Thanks a lot to the organizers for inviting me to CoRL this year. Today, I'd like to give a tutorial on safe reinforcement learning. Just a few words. So this is based on a joint presentation with my former PhD student, Felix Berkenkamp. And so a lot of credit really goes to him. I'd also like to say that this is a super active research area with a lot of really smart people working on it, and with a number of researchers who've made similar contributions to this area actually at this conference. So I'm very much looking forward to further exchange. It's also a very much emerging area with lots of exciting open questions. I've tried to break it down a little bit, also leave you with lots of references. Of course, in a short time, I'll not be able to cover all these aspects exhaustively, but hopefully we'll get enough to have some nice discussions. Okay, so let's get started. Given the audience, I probably don't have to say too much about what is reinforcement learning. So it's the abstraction of sequential decision-making under uncertainty that is an agent situated in some environment which it can affect by carrying out some actions, and those might cause the environment to change its state and the agent to derive some reward from it. And of course, the trouble is that the agent doesn't know how the world works, so it needs to deliberate between exploration, so experimenting with different actions to learn about their consequences, as well as exploitation, using what it learned in order to do well. So this is a setting that's been extensively studied for several decades, both in machine learning, but also in control theory, so that approximate dynamic programming, adaptive control, and so on. So it has really a rich history, but we've all seen these amazing recent advances, and especially in the context of deep reinforcement learning. And you can't really talk about RL these days without just being impressed by the accomplishments that DeepMind had with their AlphaGo and AlphaZero agents in the game of Go. Now, these advances certainly created a desire and an appetite to use reinforcement learning to increasingly higher stakes real-world applications, such as autonomous driving, medical applications, aerial robotics, and other applications such as controlling our infrastructure. Now, I would argue, and I think many of you would probably agree, that there's quite a substantial gap between these situations where RL has been working super well in the past and a lot of the domains that we have on this slide here. So in particular, the settings where we really have seen a lot of advances in RL are situations where we have a perfect computational model of the world. Games are maybe the best example of this, right? So we know precisely how the Go board looks once we and our opponent have taken our moves. And so that means that exploration is primarily a computational concern. It's a really difficult one. There's massive state spaces, and it's really impressive what can now be done given massive compute and advances in deep reinforcement learning. However, a lot of the applications that we've mentioned here don't have a perfect computational model of the world. So we might really have to work with situations where these learning agents make decisions in the real world. And as these stakes of these applications are quite high, we really want to make sure that these agents act in a safe manner. So when I talk about safe RL, I really mean this higher level questions of how can we think about agents that learn to act safely in a priori unknown environments. So I'd like to just briefly talk about a few applications that we've encountered in our research, and we'll talk about a number of others that I explored in the community going forward. So here's one that stimulated a lot of the research that I'm going to talk about in the second part of this tutorial, and that's a collaboration with Joel Burdick's research group at Caltech, who in turn works with clinical collaborators on the problem of spinal cord rehabilitation. So they work with spinal cord injured patients. And what was found is that by implanting these patients small electrode arrays that you can see on this X-ray image here and applying carefully chosen low levels of electrical stimulations, some of these subjects regain remarkable levels of bodily activity and control. And so now, of course, one challenge is that we don't have a perfect computational model of a patient, and patients react differently on this trade-off, to this treatment. So that means that any sort of learning algorithm that explores this large space of possible stimuli will really have to explore in the context of clinical trials. And I'll talk about some algorithms that later on actually have been used by Joel Burdick and his collaborators on the actual clinical setting. Now, given that this is the conference on robot learning, I'll also talk a little bit about robotics. So I'm not a roboticist myself, but I really like collaborating with roboticists. And this is a particular collaboration with Angela Schöllig, who is also the PhD co-supervisor of Felix. I'm also going to talk about one application. This is a large collaboration with the Paul Scherrer Institute. That's a large research facility in Switzerland. And we use ideas from SafeRL and Safe Bayesian optimization to tune their SwissFEL free electron laser. So this is a 700-meter long linear accelerator that generates X-ray pulses of extremely short duration, so femtosecond duration, 1/millionth of a billionth of a second. And using this instrument, experimenters can image extremely fast processes, like molecules turning from one into the other in the context of a chemical reaction, which has lots of applications, say from drug design to materials discovery and many others. So what's the plan for this tutorial? So if we talk about SafeRL, we of course have to at least start talking a little bit about what we mean by safety, talk about safety specifications. Then we'll review very briefly about basically how to act safely in known environments, which of course is a big research topic on its own. But then we'll focus primarily on the challenges that arise when going to unknown environments. And a specific focus in the second part of this tutorial is going to be techniques of safe exploration. By the way, feel free to ask questions as they arise. So I'll do a short break in the middle where there's time to ask questions, but also feel free to interrupt before. Good. Okay, so let's start with saying what we actually mean by safety. So let's start with a cartoon. Suppose you have this quadcopter that's supposed to accomplish some task. Maybe go to the goal, and along the way it carries out some trajectory, some sequences of state actions, and we have to ask, is this trajectory safe, right? And presumably you don't want the robot to crash against the ground. You don't want to crash against the wall or some obstacle. And now one way to encoding this is using constraints. So you can imagine having some function G called safety function that takes a candidate trajectory tau and assesses how safe that resulting trajectory is. In principle, that could be a Boolean predicate. Oftentimes, it's really a real valued, without loss of generality, scalar function that we just indicate positive values with safe behaviors and negative values with unsafe behaviors. So in this concrete example, G of tau might just measure the closest proximity we ever have to any obstacle. Now, of course, specifying such safety constraints is highly application specific, as is the design of reward functions in reinforcement learning, and as such also already a very difficult topic. So what I just want to do is I want to point out that there's a rich literature really thinking about ways of how to encode using formal languages different kinds of safety specifications, and then maybe using techniques from formal verification in order to verify whether these assumptions actually have been met. So there's a lot more to say about how to specify safe behaviors, but I'm not going into much more detail but rather we'll see some concrete examples in later applications. Good. So if you go back to our RL loop, we now want to constrain it in a way such that the trajectories we encounter are safe to satisfy these constraints. The trouble, of course, is since our agent doesn't know how the world works, it can't just choose a trajectory, right? So it can only choose a policy which might carry some uncertainty about what sequence of trajectories we are actually going to visit. And that's, of course, where the key challenges really arise, that the effective constraints we have to deal with are not really known ahead of time to the agent. So it means that now we have to somehow take the safety specification of individual trajectories or behaviors and turn them into some objective that we can incorporate in optimization. And of course, there's also various different ways of doing so. So we might, for example, ask that no matter what, we want to make sure that all trajectories we can possibly encounter are safe, right? So thinking about the worst case realization of this safety function. And now in situations where the model is really quite well specified, maybe you have some bounded disturbances and so on, one can use ideas from formal verification, robust control, and so on in order to guarantee really worst case safe behavior. Now, in a typical setting of reinforcement learning, where there's a lot of uncertainty about the consequences of actions, typically requiring trajectories that are safe even in the worst case is typically too much to ask and often leads to extremely conservative behavior. So if you want to go away from it, you have to somehow talk about uncertainty quantification now. And of course, a standard language to reason about this is probability. That means that now we have a distribution over possible trajectories. And I'd like to point out that there's different notions of uncertainty that can factor in here. So even for deterministic systems, we might just have epistemic uncertainty about, say, the unknown dynamics of the system. But of course, we might also face explicit stochastic environments or use stochastic policies. So in the end, we're going to have now a random variable that encodes basically the distribution over our safety function value for these different random trajectories for any candidate policy. Okay, so which might have, say, a distribution that looks like this. And we now need to quantify it somehow. One way to do it, of course, is to look at the expectation and ask that the system is safe in expectation. So require that the mean of this distribution, say, is above 0. Now, of course, that can lead to some undesirable consequences. So you can have situations, especially if this distribution over our random variable G is multimodal, you can have situations that you're safe on average, but most trajectories are actually unsafe. Now, of course, one can think about other ways of taking this distribution over these possible safety values and quantifying the risk in a certain way. One way to do so is to, for example, require that most trajectories are safe, right? To bound the failure probability, which basically means that we're now going to put a constraint on a pessimistic estimate on this random variable G, or a lower confidence bound on this random variable G. We might, for example, say that we want the robot to crash at most 10% of the time, or probably have more stringent safety requirements. Okay, so this is now a way to sort of turn safety into a set of constraints. And now what we'll see later on in this tutorial is actually a range of techniques that basically operate using this notion of value at risk and use ideas from formal verification, robust optimization, where now we don't constrain the worst case over all possible trajectories, but only over all plausible ones that are sufficiently likely. Okay, so this is the value at risk. I also want to point out that, of course, there's a lot of other risk measures. So one popular one that's widely used is the conditional value at risk. It's the lower bound on the value at risk. It's the expected value conditioned on being in the tail. So the average over the tail of this random variable within this alpha F percentile of the values it can take. And that's notion of risk has a lot of desirable computational properties. So one can, for example, under some circumstances, relate it to an expected notion of safety with a certain transformation applied to the returns. And this idea has been widely used in various different fields, mathematical finance, but also in robust reinforcement learning and so on. I'd also just like to point out, so there's actually 2 papers at NeurIPS coming up this year on looking at algorithms for doing really stochastic large-scale optimization with this criterion, really pushing the boundary of models that can be optimized with it. Good. So we've seen a bunch of different notions of safety. both in sort of the worst case and the stochastic setting. Of course, there's more than we can review here, right? But we've talked about some of the important ones. And of course, which one to pick depends on requirements of specific applications that we might face, but also, of course, any sort of knowledge or prior knowledge we might have about the system. Of course, the choice of these different notions of safety also has important algorithmic consequences in terms of our ability of solving the resulting approximate dynamic programming problems. So this leads us to this question, how to act safely in known models. What I mean by a known model is that you now actually have a model where all the uncertainty is well specified. So for example, a Markov decision process where we have given certain constraints, or maybe a deterministic system with certain sets of disturbances that we possibly can consider. And so now, depending on which notions of safety you consider, there's a whole range of different solution techniques. I just want to briefly mention a few. So one important one are constrained Markov decision processes. So here we typically talk about safety in expectation, that a safety function similar to the reward decomposes additively across different time steps. And this additive decomposition and linearity of expectation then allows to use similar techniques that can be applied in the unconstrained setting, for example, P-based solution techniques or other approximate dynamic programming formulations. Of course, robust control, looking at the worst case over a set of disturbances, is extensively studied, agent fidelity control, and so on. And there's a lot to say about these sort of methods. And of course, there's ideas in between. One can combine ideas from sort of worst case and stochastic optimization. For example, optimize the expected behavior with respect to a worst case MDP out of some set of possible MDPs. So that's related to distributionally robust optimization, which is a large research area, of course. And this field of how to act basically under safety constraints under a known model is still a very, very active research area with lots of exciting advances. So as we said, we want to focus on a setting that we don't have a known model of the environment. So it means we really want to think about agents that get deployed in the real world and sort of learn by acting, okay? And so that means that our poor agent now doesn't know about the consequences of the actions, can't simulate forward what might possibly happen. And of course, this is where the real challenges arise that I want to focus on in today's tutorial. So now the first question, of course, where do we even start? Literally, where do we start, right? What's even the first policy that we can deploy that nothing bad happens? And so it's pretty obvious that without any sort of prior assumptions, it's completely impossible to act safely, right? So this should be pretty clear. So the main question really is, what are different ways of infusing prior knowledge in coming up with the first feasible policy to solve sort of the feasibility problem? And I want to talk about some ideas that have been explored in the literature, besides sort of explicit construction of first principle models. And so one important area, of course, that's been quite widely studied is imitation learning. It's a large research area on its own, where prior knowledge comes in form of a human expert, say. Okay, so there's an expert that has in their head a safe policy, pi star, that would prescribe a safe action in any state, and we can query this expert for advice. Now, how does this work? So you would start maybe with some training data set of a bunch of different demonstrations, basically trajectories labeled by the human expert. And then given this data set, we can try to learn a parameterized policy, say parameterized with a neural network, and try to basically solve a supervised learning problem that we try to predict the expert's action for any given state. Now, of course, the key issue here is that we immediately leave the IID setting and there is a substantial domain shift. So while we are close to states where we have labels by the human expert, things are fine. As soon as we deviate from those states, the policy is going to do something crazy and the agent is going to not do well. So now, there's, of course, this is a classical problem in imitation learning, and there's ways to fix this. In particular, by keeping the sort of collecting more and more data. And so techniques like data aggregation and policy aggregation. So I just want to talk briefly about data aggregation. Here, the idea is that instead of just solving the supervised learning problem once and deploying the resulting policy, what we're actually going to do is we're going to roll out the policy, but then ask our expert again to obtain new labels for the states that this policy visits. And then, of course, we're going to update the policy and iterate. And so now one can analyze this resulting algorithms using ideas from regret minimization and actually show that under some conditions, this is guaranteed to have low regret, to actually converge to a good policy. Now, so far in the basic setting, safety doesn't really appear. So here it means that when we roll out the policy, it might very well happen that bad states are being visited, right? And safety constraints are violated. And so there's quite a bit of really interesting recent work on thinking about safety in the context of imitation learning that I just want to point out. And so here, one basic idea that's been explored is to not just blindly apply the policy that's learned, but basically try to figure out when you can trust it. So for example, one can try to have a separate learning model that tries to predict whenever the learned policy is going to produce an action that's close to the expert's policy. Or one can also try to quantify the uncertainty in the prescribed action by the policy and then require, for example, only play the action when the policy is sufficiently confident about what the correct action is. So in sort of the cartoon picture here now, we follow our rolled out policy in red. At some point, we detect that we are doing something bad. So we're deviating from where we know what to do. And at that point, we relieve control to the human expert to collect more data. And then, of course, the hope is that eventually, as we collect enough data, the expert is asked as little as possible. Okay, but so that's different models that have been explored here. There's many interesting open questions in this context of safe imitation learning. So another idea that we've been recently exploring, that's a paper coming out at NeurIPS this year, is to use a different form of domain knowledge and infusing it using concepts of curriculum learning. So this is sort of inspired from how basically little kids learn without failing. So if you think about children learning how to ride a bicycle, they typically are given some help, right? So maybe the supervisor would hold them and try to make sure they don't fall or give them training wheels, etc. So the question is, can one sort of have training wheels for reinforcement learning algorithms? And here's sort of a little illustration of how one can think about this. Here, this is the illustrated in the lunar lander environment. So we want to learn this stylized spaceship on this planar surface on the moon. And so now this is not a very difficult RL problem, but it's a difficult one to learn without crashing. So now what you could imagine is instrumenting a set of training environments before the policy actually gets deployed, where, for example, detect that the agent enters some bad states and apply some sort of intervention. So for example, as soon as the agent here leaves this particular funnel, it would be reset to a state that's close by. So that's one possible intervention. Of course, there's many possible interventions. And now one can think about sort of this meta problem on how to optimize over curricula of such possible interventions. And so now, in contrast, if you sort of start just solving the original MVP, it can solve the task quite well with lots of reward, but it would fail very, very often. And now by applying these different interventions, you avoid most of the failures. On the other hand, learning gets harder and also returns get smaller. And these depend on sort of these different interventions. And by optimizing of these curricula, you can basically get back the same performance without failing along the way. So this is sort of a different way of how one can think about infusing prior knowledge, where maybe at the training phase initially, one can sort of instrument the environment in different ways. Okay, so now we have some initial safe policy. The question is, how can we do better, right? So we have a feasible policy, but we want to find a good one, right? We want to optimize performance in some way or the other. Okay, and so now that's sort of the next question. And for the rest of the tutorial, we'll explore various different ways of how to do so. So I'll first briefly talk about some set of techniques that rely on certain types of prior knowledge, again, in order to basically allow the agent to use learning to deviate from the initial safe policy while ensuring that bad states are not visited. So let me just sort of illustrate this. So suppose we are sort of in a situation where we actually know and we can diagnose when bad things are about to happen. So here's sort of this cartoon illustration, right? You sort of see this quad cup that's close to sort of crash against the wall. And now what we can try to do is we can try to think about sort of an architecture that we wrap some safety mechanism around the learner, right? So that we have some sort of safety controller that then gets to take over before the agent crashes against the wall, and then relieves control to the learner again, as long as it's safe to do something. Okay, so this basically allows to use this initial safe policy, inject a bit of learning in different ways, but then sort of create this boundary, a shield, a filter around it in order to avoid bad things happening. So here one can sort of think about essentially a form of robust control where the learner is seen as some sort of disturbance that has to be taken into account. And there's a range of really exciting work that explores various different facets of this concept that I'll not be able to review here in much detail. So there's ideas like shielding or safety filters that have been explored and are very effective for such settings. So this is a way of incorporating certain kinds of prior knowledge, not just when coming up with the initial policy, but also to sort of isolate learning in the context of the larger system to make sure that the effects of the learner are bounded and can't lead to disastrous consequences. So another interesting related concept that's been explored by Yisong Yu and his collaborators is, instead of using hard constraints on the allowed policies, is to use the idea of functional regularization. So instead of optimizing simply the performance, say, of a policy, you would also add some regularization term that inject certain types of control theoretic prior knowledge. So prefers certain policies that, for example, are smooth or satisfy certain stability properties and so on. And so here are some relevant papers on this line of work, and also there's some cool applications that Yisong and his collaborators have been looking at in the context of simulated car racing or controlling autonomous robotic cameras for optimizing news coverage in sports. So basically, these approaches are different ways of essentially using prior knowledge to sort of shield or bias the learned policy in some way or the other. But of course, you somehow need to have this kind of domain knowledge as a constraint. So now, of course, the natural question is, can you reduce this dependence on prior knowledge somehow? And in the following, we want to explore some ideas that go in this direction. So so here let me start to talk about one such approach, which is specific to expected safety as a criterion that we had talked about, say constrained Markov decision processes, for example, as we had talked about. Okay, so suppose again, we have our initial safe policy, theta B, our baseline policy that we can deploy, and we care about say optimizing its performance. So for sake of this presentation, I'll actually set the performance objective equal to the safety function. But of course, one can also separate these two objectives, and that's been studied in the literature as well. So safety basically requires that whatever policies we consider deploying on the real system, theta, we want to ensure that with high probability, the performance of this new policy is at least as good as the baseline policy, with some high probability that we get to specify ahead of time. So it's really a conditional expected safety. So expected safety criterion, but we want to bound the failure event where this happens. Okay, and so now what we would like to do is we want to avoid using prior knowledge, but one way to replace prior knowledge is prior data. So you can, for example, take a look at trajectories that are collected from this safe baseline policy. So for example, we can run this baseline policy to now get sort of a distribution of our possible trajectories. And now we can try to use this data in order to evaluate a new policy that we're considering. So this is an area called off-policy policy evaluation. It's also a super important, exciting subfield of reinforcement learning. So we want to ask what do these observed trajectories tell me about the performance of some different policy that we consider deploying? And there's a class of techniques that basically revolves around importance sampling and variance of this. So what we can do is we can, if we care about the expected performance with respect to a new policy, we can simulate according to our safe baseline policy and then apply some importance correction in order to get unbiased estimates of the original objectives. Okay, and now this importance correction crucially can be computed purely based on knowledge in the policy. So the probability of different actions that are being chosen under different states. So now this is sort of the most basic idea. There's much better ways of doing this. So a crucial concept to look at here is this notion of eligibility traces. Okay, so now using this, we can sort of try to ensure guaranteed improvements of our policies. So what we've discussed is how to obtain unbiased estimates of J of theta. But of course, there's going to be a potentially significant variance in these estimates. And so now a key question is, if you want to ensure that we improve with high probability, then we somehow need to estimate something beyond expectations. And what one can, at least in principle, do if there's, say, bounded values of our function g or j, then we can use concentration inequalities in order to obtain confidence estimates. And those basically allow to obtain statements of the kind that you can lower bound with high probability the expected performance or expected safety of some new policy as this importance corrected unbiased estimate minus some term that does depend on the number of samples that you've used. Okay, and so the overall setting would sort of look like we simulate forward these trajectories according to the baseline policy to get a training and a test set. You would maybe optimize over candidate policies in the training set, and then evaluate them in the test set, and then use policies only if you're confident that they're safe. Now, of course, there's many details to this. So these ideas have been studied quite a bit in the literature. So first, this basic idea of essentially constraining, so obtaining these of policy estimates, but then also thinking about solution concepts. So how to now optimize policies under constraints that basically of the kind that we have described before. Okay, so this is basically the first part of what I wanted to cover. So we reviewed some of the basic safety definitions, both in the stochastic and the worst case setting. We identified as sort of a first challenge, this key issue of how to come up with a first safe policy, and then started to explore different ways of how we can now sort of integrate learning on top of this first safe policy in order by using either prior knowledge or using data from a baseline policy in order to improve performance. What you want to do in the second part of this tutorial is to explicitly look at this challenge of safe exploration. So maybe now is a good time to just take a few questions, and then we can continue with the second part.
Great. Thank you, Andreas. There's also a first question in the Q&A. So how can you apply the curriculum intervention idea in an actual system where you can't do an intervention? So for example, an autonomous car versus the lander setup where you can. Sure.
So it's a great question, right? So basically, whether one can do these types of interventions very much depends on particular applications at hand, right? And that is something to be investigated in future work. So here we look at the basic concept in these simulations and do a bit of theory in this context here. Maybe one thing to point out, so this curriculum learning idea can already be very valuable in order to solve challenging constrained MVP problems, even to come up with feasible policies for constrained MVPs, and we demonstrate that in the paper.
Okay, great, thank you. Are there any other questions that people would like to post? For the moment, I don't.
Okay, so then.
Any. Okay, good.
I'm happy to continue, right? And we can feel free to interrupt me anytime. And of course, there's more time at the end. Good. So let's talk about safe exploration, right? So it means that we want to learn how to act in these unknown environments. We now have some sort of policy that is deployed on the actual robot. and now the actual system that we control, we collect some data, and from that we would update the policy. And of course, now the question is, how do you collect good data in order to find good policies? And so now to dive deeper into that, so there's different settings, of course, that are studied in reinforcement learning, both the model-free and the model-based setup. In the model-free setup, we consider some parametric family of models. And what we would do is we basically try to solve this global optimization problem over the parameters of our policy in order to optimize the performance. And of course, in the model-based setup, the idea would be to, based on data, learn a model of the environment and then plan accordingly. So I want to, so the mechanism that we'll be exploring to encode safety here is to be explicit about the uncertainty, both in the objective and the constraints, and then use this uncertainty in order to ensure constraint satisfaction with high probability, effectively placing a bound on the value at risk. So I'll start illustrating this idea in the model-free setup, in particular in the context of safe Bayesian optimization. And then later on, we'll talk about the model-based setting. And so here, let me just, as a concrete motivating example, come back to this problem of how to tune the Swiss-fell-free electron laser that I briefly talked about at the beginning of this tutorial. So this is a pretty complicated machine with a lot of literally moving parts. So the electron beam properties are shaped using a number of different magnets that can be controlled in real time. And the beam properties very subtly depend on essentially the configuration of these magnets, as well as additional environmental properties like temperature, humidity, and so on. So they basically need to be adapted continuously over time. And there's also often typical different application requirements in terms of beam properties that the policy need to adapt to. Now, there's also safety constraints. So if we're not careful, what can happen is that there can be beam losses that might cause damage to some of the magnets of this system. Of course, that would be super problematic if that were to happen. Of course, there are some safety mechanisms in place that will just shut off the machine, but you also don't want that to happen during live experiments. This experiment time is really expensive. So in order to detect possible constraint violations, so basically the corresponding safety specification is through beam loss monitors. So these are basically monitors placed throughout this device that actually measure whether there are beam losses and effectively allow you to monitor how close you get to violating any of the constraints. And so now basically we can sort of think about this problem as essentially a sequential decision problem where every round theta t, we inject some parameters on how to configure our magnets. Then we get a noisy measurement of the beam performance. That's our reward. At the same time, we get a noisy measurement of our constraints. Here in this case, reported by these beam loss monitors. And given those observations, we want to decide how to proceed, right? What next configuration to propose. And of course, the goal is to solve this constraint optimization problem where we want to maximize performance subject to these constraints. However, we want to ensure safety, not just at the end to find eventually a feasible solution, but we want to guarantee feasibility of all iterates. So every single experiment we carry out has to be safe with high probability. So basically, we have to solve an a constraint optimization problem with an unknown objective and unknown constraints that can only be accessed up to noisy thorough order feedback, so noisy measurements. And we want to guarantee feasibility every step along the way. So in general, of course, this is a completely hopeless task. So we need to figure out when one can actually try to make progress with the setting. So here's sort of a cartoon picture to illustrate some of the concepts. So the x-axis is now the set of parameters. The y-axis is the performance, which for sake of simplicity is just set equal to the constraints. And so that means we want to maximize j of theta, basically, while ensuring that wherever we evaluate the function, we're above the safety threshold. Now, without any prior knowledge, even the first action could be unfeasible. So we make the same assumption as we've discussed in the first part of the tutorial, that we have some initial safe seed for exploration, so safe feasible initial policy, indicated by this cross here. And starting our exploration from there, of course, ideally, we'd like to find the global optimum. Now, it should be pretty clear that in general, this is not possible. without any assumptions on the shape of these objectives, this is a hopeless task. So we'll have to make some sort of regularity assumptions, and I'll be more specific about those. But even under some sort of regularity or smoothness assumptions, we can't really hope to leave this red set here, which is the connected component of the feasible region that contains our safe seed, our starting point for exploration. And so the benchmark that we're going to compare to is the reachable optimum, which is the global optimum of this red set, or for high dimensional settings, we can really only hope to get to local optima on this red set. Okay, so now how do we encode prior assumptions on the objective and the constraints? So one way to encode prior knowledge is to take a Bayesian approach and basically view our objective and constraints through the lens of a probabilistic model. And that's exactly what's done in the field of Bayesian optimization. So we would treat the unknown objective as a random function drawn from some distribution over functions on which we can then condition to make predictions, not just with respect to the performance of experiments we haven't carried out, but also quantifying the uncertainty in the resulting prediction. And now this distribution can now be used in order to come up with a surrogate objective called an acquisition function, which allows to navigate the exploration-exploitation dilemma. And so there's a whole range of different acquisition functions that are used in Bayesian optimization, both in the unconstrained and the constrained setting that I can't review in detail here, but I want to explain some of the most important ideas. So first of all, we have to specify what kind of probabilistic model we're going to use. In the illustrations, we are going to use Gaussian processes. That's maybe the default choice in Bayesian optimization at the sweet spot between expressiveness in terms of applications, but also tractability, both computationally and mathematically. But in principle, many of the algorithms can also be used for other models like Bayesian neural network models and have been used in the literature. So as a Bayesian model, once we carry out experiments, we can condition on them to get a posterior distribution that contracts given more and more data. Right? And now the smoothness of that resulting function or the regularity conditions are imposed through the covariance function of this Gaussian process, which basically expresses prior knowledge on the strength of correlation or covariance of the function response between pairs of inputs. So this tells us everything we need to know about smoothness of this resulting model. So how is the uncertainty useful? Here's sort of a key picture. So suppose we've carried out a bunch of experiments shown by those pluses here and calculated our posterior distribution with mode given by this black line and uncertainty given by these gray confidence bars. And suppose we are in the situation where with high probability, the true function lives within these gray confidence bounds. Then we can apply the following rationale. So we can look at the best lower bound, so maximizing the lower confidence bound of this model. And now if the model is well calibrated, so the true function is contained in these confidence bounds, the maximum must be somewhere within these green regions where the upper confidence bound exceeds the best lower bound. And that is often used as a justification for the famous optimism in the face of uncertainty principle in reinforcement learning, which just places the point that maximizes the upper confidence bound. However, if safety is in place, maybe being too optimistic is also problematic. But of course, one can make use of the same picture to also reason about safety. So if this is our safety threshold, then of course we can now look at a pessimistic estimate, say of our constraint, given by the lower confidence bound, and say focus our exploration in this red subset of the domain where the pessimistic estimate exceeds the safety threshold. So it's a conservative inner approximation of the feasible region. Now, in order to realize those pictures, we need well-calibrated confidence bounds. And that alone is a very difficult topic. But it turns out for Gaussian processes in particular, there's some results that can be used in this context. So first of all, confidence bounds for GPs are simply mean plus a multiple times the standard deviation. These enumerate percentiles. But now, if you want to rely on these confidence bounds algorithmically, we need to make sure that they're calibrated in a way that they hold uniformly over all iterations of the algorithm and everywhere where the model uses them in order to make predictions, right? So essentially, that's sort of a massive multiple hypothesis testing problem that we have to correct for. It turns out one can indeed correct basically and scale these confidence bounds, even in sort of a frequentist setting, where you don't even make a prior assumption, a Bayesian assumption about the unknown function, you have to scale the function such that the unknown objective sort of agrees with your prior, and that sort of agreement can be measured in terms of the complexity of the unknown function, evaluated according to the reproducing kernel Hilbert space norm of this unknown function with respect to the covariance function that the Gaussian process uses. And then there's a second term that depends on the capacity, so that the admitted degrees of freedom of this Gaussian process model, which can be numerically accurately computed for any given kernel and can be analytically analyzed, both using ideas from submodular analysis. So there's quite some literature on this. I will not go into much more detail here. There's also some recent work that looks at, for example, adversarial perturbations and misspecification in these sort of settings. So what matters for us is that at least under some circumstances, we can really understand under which conditions we might be able to get such well-calibrated confidence bounds for GPs. And one way of using them is the safe-opt algorithm. So it basically uses the Bayesian model for our objective and our constraints. So we want to make sure that wherever we evaluate, we're safe. So G of theta is above the threshold. So we're going to use our prior on J and G. And now we use them in order to come up with our safe set, right? The conservative inner approximation in red, as well as the set of plausible maximizers. And now in principle, what we could do is we could just say, let's be optimistic, but constrain our choice to this red subset of the domain. The problem is that this strategy very quickly gets stuck in poor local optima. And the reason for this is that the set of plausible maximizers in green is typically contained in the strict interior of this red set and has no incentive to push the boundary to try to figure out different areas in our parameter space where we can achieve improved performance. So we also need to look at some notion of expanders, so indicated by those purple points. Intuitively, these are points close to the boundary where observations plausibly allow to infer that additional actions are safe. And now basically among those points that are relevant, plausibly optimal or expansive, we pick the ones that provide as much information as possible. And eventually we figure out that better solutions are actually found over here. Okay, so that's the safe-opt algorithm. And under the kind of conditions described before, as long as the confidence intervals are well calibrated, one can guarantee both safety and completeness for the resulting algorithm. So guarantee that the algorithm will never make an unsafe decision. And one can even analyze sample complexity, so bounds the number of iterations it takes to get an epsilon optimal reachable point of this algorithm. Now, I'd like to say, if you ask really for global optimality on the safe set, then there's constants here that are exponential in the dimension, and that's impossible to avoid. However, if you're happy with locally optimal solutions within the safe set, then one can get away with polynomial dependencies. So there's work on this. So that's the first reference, and there's quite a number of other approaches that have been exploring related ideas in the literature. So here's the first demonstration of this that Felix did a few years back in Angela's lab on a simple quadcopter task. So this quadcopter here just flies from A to B. So we start with an LQR controller as our initial safe policy that's derived from the first principle model, which is chosen conservatively. So it gets there, but is not very efficient. And now what we do is we inject some controller gain parameters and use safe Bayesian optimization in order to tune them online in order to optimize performance under constraints. I'd like to point out that most of these parameter settings will immediately destabilize and crash the robot. So if you just play optimistic exploration, for example, then you're being too optimistic. So I'll just let this run for a little longer, and then we see a quick comparison, and then we'll move on. So this is, so you basically, the algorithm allows to sort of gradually enable less and less conservative behavior as more and more data is being collected. So as mentioned, here are some results on this spinal cord therapy application. So as I mentioned to you, so Joel and his collaborators, Yanon Sui, Zhang, and Yue, applied a variant of the safe-opt algorithm called stage-opt, actually in the context of clinical trials, and they were able to actually find recommendations for stimuli that performed as well or even outperformed the best choices found by the physician. So I very much encourage you to take a look at that paper. So here some results on the Swiss free electron laser that I mentioned to you before. So here we use a variant of the algorithm that's designed to scale to much higher dimensions. So we address it here to a few tens of dimensions that we tune live using this algorithm by using randomly chosen subspaces and applying the algorithm on those randomly chosen subspaces. And there's a convergence analysis in our ICML paper describing this algorithm. And so here, the sort of experiment that we would do is we would take expert settings given by the physicists. We would adversarially detune them so that the laser has bad performance. And then we would use different algorithms in order to try to recover high-performing parameter settings under these safety constraints. And so in most cases, the algorithm is not only able to recover parameters as good as those by the human expert. Sometimes they even outperformed the parameter settings that were found by the expert, and also outperforms standard local search techniques that are used in this domain. Good. So this is some ideas on safe exploration in the Model 3 setting. And so one thing I'd like to point out that essentially all the work that I've described so far focused on the so-called episodic setting, where we're actually able to reset the learning agent safely to some starting state. So repeat the same experiment, and we sort of want to find settings that optimize performance while satisfying safety constraints. But of course, many really important challenges arise if you can't reset the agent and if you really have to plan ahead and have to worry about reachability. So in the last few minutes of this tutorial, I want to talk a bit about techniques of how to reason about ergodicity of the resulting behavior, reachability, and so on in the model-based setting. Okay, so now, as you said, we want to look at the model-based setting. That means that the data we get through our exploration, we want to use to learn our model. And our safety, basically, again, we want to make use of uncertainty in that model that we want to learn. So we're going to learn probabilistic models. And we use the uncertainty in the model in order to ensure safe behavior, similar to what we had to describe just before. Okay, so how does this work? So we first have to start with certain modeling assumptions. So here we'll be thinking about nonlinear dynamical systems, where at any state ST we apply some action AT, and the model would basically prescribe the next state that we get to. What is often done in the literature is to assume prior knowledge in form of some first principles a priori model, and then learn disturbances or basically unmodeled behavior discrepancy between the first principle model and observations from data using an unknown model that is then learned. And the set of approaches that we'll focus on here now also use Gaussian process models for those resulting dynamics. And such Gaussian process dynamic models have a very rich history and have been extensively looked at and studied in the literature. So how would they look like? So now if again, in this one-dimensional cartoon, the x-axis is our state action pairs, and the y-axis is now the ST+1, so the consequences of our actions. We would have our unknown function as shown here. We have our a priori model given by this mean function of the Gaussian process, and then we have some uncertainty around it. Given data, our uncertainty contracts, and we gradually learn more and more accurate models. And as a consequence, as the uncertainty decreases, this reduced uncertainty will allow less and less conservative and higher performing behaviors. So I'd like to point out that there's a lot of really exciting work exploring such learning-based approaches, especially in the context of model predictive control. And so I only have limited time in this tutorial, so unfortunately I will not be able to present all this work, but here's references that I strongly encourage you to take a closer look at. I'll talk about some of these approaches going forward, but there's just so much exciting work that's really hard to portray in such a short tutorial. So first, I'd like to talk about some early work on using such learning-based model predictive control in the context of autonomous driving, just with a little bit of a motivating example. So here's first some work from Angela Schoenig's group. So they use an outdoor robot. They use Gaussian processes to forward predict plausible dynamics. So initially, the model is quite unsure. So the robot has to drive very slowly to ensure safety with high probability going forward. And then as it collects more and more data, the model becomes increasingly confident about its prediction, hence enabling faster driving, right, and higher performing behavior. And so there's also some super exciting work in Melanie Zeilinger's group using these ideas for autonomous racing. So some really cool papers to read in some more detail. So in the following, I want to talk about some ideas of how one can analyze and make certain safety guarantees about such learning-based control algorithms. And I just want to illustrate them in terms of this really stylized cartoon example, the RL 101 task of a cart pole that should reach some target destination, preferably without the cart pole falling down. And so now what we would like to do is we would like to plan how to behave by making use of the uncertainty that we get out of the probabilistic model. So here's sort of a cartoon picture. If this is our state space, there's some set of states that we don't want to get at. So typically in the setting, the safety specification comes from some explicit specification of a set of unsafe states, or state action pairs. Now, if you have our agent in some state, we can consider planning forward for some time steps. And since we have uncertainty about the resulting dynamics, there's going to be some uncertainty where we are certain time steps ahead in the future. And now, as long as we use well-calibrated confidence bounds, and we can ensure that these confidence ellipses don't fall into this unsafe subset of the state space, then at least within those time steps, we hope that nothing bad happens. Then, of course, as the agent collects more and more data, the model becomes more and more confident, and hence the uncertainty in the prediction gets smaller and smaller, enabling more and more aggressive behaviors. Okay, so now in order to make this a bit more concrete, one has to first talk about how to even forward propagate these uncertain nonlinear dynamics, and that's generally not an easy task. So we use, if you use, for example, GPs, then the one step ahead predictions, they are Gaussians, right? They're ellipses. But if we iterate them only 2 steps ahead of time, we send these ellipses through nonlinear functions, and they get twisted in a pretty nasty fashion. So one way of dealing with this is to think about conservative over-approximation. And so that's something we looked at in a recent CDC paper to get provably conservative over-approximation of these confidence bounds. But there's also a lot of other ways of how to think about this also in the case of stochastic dynamics, or in the case when one, for example, forward propagates moments of this distribution and so on. Okay, now one challenge is that planning ahead a finite number of time steps may not be sufficient. And here's sort of the picture again in our cartoon example. So while those states are all safe, so the cart pole hasn't fallen at any of those states yet, for those last 2 states here, no feasible control will ever allow us to go back to an upright position, and the cart pole is bound to fall down eventually. Okay, so that means that now we really have to reason about reachability and connectedness, godicity, etc., long-term consequences of those actions. So it's not sufficient to only plan ahead for some finite number of time steps, but we need to reason about long-term behaviors. But fortunately, one can use these confidence bounds even to reason about infinite time and long-term safety properties. And I want to illustrate one way of how to do so using the specific notion of stability as our notion of safety, and using the idea of Lyapunov functions to verify stability of nonlinear dynamical systems. So of course, that's a classic concept from control theory. So here's our state space in a one-dimensional cartoon. Suppose VC0 is a set of states that we have a policy that we can always stay within the states, the set. So it's so-called control invariant set. So for example, this is a set of states, so we can always stop the car and remain standing. And now what we would do is we would take a Lyapunov functions and positive definite function VS, and look for level sets of this Lyapunov function. So basically subsets of the domain where we are guaranteed with the given policy pi to always go downhill on this Lyapunov function. So if we can ensure this one-step decrease condition, so that this Lyapunov function is guaranteed to decrease for our policy f under our model, for the policy pi under our dynamics f, then we can conclude from this one-step decrease condition, so a one-step property, one can guarantee basically stability for the long-term dynamics. So of course that's a super influential, extremely important idea, and also has been explored quite a bit in the context of reinforcement learning. And now one can use these confidence bounds that I've described in order to verify stability for all plausible dynamics. So if you now have, say, our first principle model and some unknown dynamics, G, that we only have some confidence bounds for, then what one can basically do is to verify the decrease condition with high probability, basically for all plausible dynamics that lie in this confidence interval. Okay, and so then this allows to certify long-term properties like stability, even looking at just these one-step predictive confidence intervals. And now one can put all of those together, for example, in the context of model predictive control. So if you have our region of attraction, so this control invariant set, now we can basically two things. We can basically simultaneously plan a safety trajectory, one that's guaranteed for to always take us back into this safe region, and at the same time, an exploration of performance trajectory that is meant to, for example, collect useful data or optimize stage costs. And now by tying them together at the first action, we can rest assured that no matter what happens in this first step, as long as these confidence intervals are well calibrated, we can follow, in the worst case, the safety trajectory. Otherwise, we can hopefully continue our performance trajectory and learn more and eventually achieve less and less conservative behaviors. And so under those conditions, basically the same regularity conditions that I've described before, one can then actually certify high probability stability guarantees and safety guarantees for this resulting system. Now, one key challenge here is really how to scale to more complex and high dimensional systems and domains. And that is really a very active research topic with lots of really interesting open challenges. I just want to point out one recent result. So it's a paper coming up at NeurIPS this year as well, where we focus on optimistic exploration using confidence bounds. And we show how one can reduce the intractable problem of optimistic exploration and deep reinforcement learning to a much more tractable sort of expected performance objective on a different policy space, so just using standard policy search techniques. So that brings me to the end of the tutorial. I just want to briefly point out some work that's super important, but we didn't get a chance to talk about in more detail. So first of all, there's a lot of really interesting very recent work looking at learning theoretic results even for linear systems. So here we focused on nonlinear systems, but there's some really exciting recent work on also linear dynamics, for example, using ideas from regret minimization and many active developments there, and also ideas generalizing beyond sort of Lyapunov stability analysis to more general sort of control barrier functions, and lots of really cool work on safe learning using control barrier functions. So that's basically it. So I tried to give you a little bit of an overview of some important elements that arise when thinking about agents that learn how to act safely in unknown environments. So in the second part, we focused specifically on challenges arising in the context of safe exploration. We talked about the model-free setting with safe Bayesian optimization, but also the model-based setting. And in both cases, the key idea is to use confidence bounds, uncertainty quantification about the unknown dynamics, unknown reward, safety function, etc., and then basically do robust optimization and formal verification with respect to all plausible dynamics supported by these confidence bounds. And this strategy allows you to then collect more and more data, shrinking these resulting confidence bounds, enabling improved performance going forward. So now where to go from here? So as I said, there's a lot of really exciting questions. So it's a super exciting research area at the intersection of many fields of inquiry, machine learning, controls, formal methods, statistics, decision theory, and so on. Lots of exciting challenges. One crucially important one, of course, is scalability. To really go to high-dimensional state and action spaces, both computationally, but also statistically. So here, you really have to think about uncertainty quantification in these high-dimensional domains, and how to do that carefully given limited data is, of course, a key challenge. Lots of interesting challenges on how to think about interaction in this context. So we saw some ideas in the context of safe imitation learning. There's lots of interesting questions there, but also say multi-agent safe learning and so on. Lots of interesting questions. And then on the more theoretical side, questions related to trade-offs between safety and performance, and of course also lower bounds on what can really be safely learned and what can't be safely learned. So with that, I'd like to conclude, and I think we have time to discuss some questions. Thank you very much for listening.
Thank you so much, Andreas, for the wonderful tutorial and giving this really nice overview of all the different flavors of safe reinforcement learning that there are. I'm sure people now have a long list of literature to go through. We already have a couple of questions that I'd like to pose. So the first one is actually related to the very first part of the second part of your talk, and the electron laser example. So here the question is for the accelerated beam tuning problem. Would the policy of don't change any parameters always be safe?
So don't change the parameters would remain safe, but would not necessarily lead to good performance, right? So as I said, the beam fluctuates quite widely depending on environmental conditions, and of course also sometimes has to be changed during experiments and so on.
Okay. And the second question is, so first, thank you for the informative tutorial. And then when you say planning, which method do you rely? Is it nonlinear optimizations of classic AI planning or something else?
Yeah, so a lot of the techniques, especially in the second part, use some form of nonlinear optimization, right? And so there's lots of different techniques that are used in the literature that I won't really give an exhaustive search over, right? But of course, also classical planning techniques are used quite a bit, especially when it comes to sort of formal verification and so on.
Right. So the next question is reinforcement learning dominant in machine learning, or is it only good for specific cases? I guess that's more of a fundamental question where reinforcement learning is placed in the big picture.
I think it's one of the exciting subfields of machine learning. And of course, it's, very closely related, not identical, right, to question studied in control, right, under different names. So I think it's a super exciting interdisciplinary topic between the different communities, and I think there has to be more exchange also between ideas between the different communities, and there's events happening where these sort of exchanges are taking place. So that's great to see.
Yeah, I very much agree. Okay, while people are thinking about more questions, I actually have one question. So, you mentioned a bit, the dimensionality, especially for, I think, for the electron laser example. And you said that you're doing this by randomly choosing subspaces. And I guess sort of in the limit, you can probably prove things, but practically, does that affect your optimality a lot? Because I would imagine this is a really large scale parameter space that you have to optimize over.
Yeah, so we actually don't choose directions uniformly at random. So we actually use informed sampling directions. So we use informed sampling, posterior sampling. So what you can basically do, so in the paper, we actually discuss various different ways of proposing these low dimensional subspaces. But one thing you can do is you can basically, if you have your Gaussian process objective for that you'd like to optimize, you can linearize the kernel around a given point and now get a distribution over linear approximations. And then one can basically sample from those in a Thompson sampling fashion and optimize with the resulting subspaces. And that often works really well.
Okay, nice. And is sort of the robustness of your optimizer, an issue. When you talk about safety, robustness is often also one, and then in the context of Bayesian optimization, is that something that you encountered?
Absolutely. So I think, as I said, this whole question on even how to act reliably on known models has many, many interesting research challenges, right? Solving the resulting minimax optimization problems. Often it's very difficult, and there's a lot of active work on how to address those at scale and so on. It's very complementary to the questions that I've focused on here in this tutorial, and I can have a separate tutorial on these types of topics. But I basically, absolutely. And also there are specific robust formulations, say, of Bayesian optimization that have been explored in the literature. So, for example, so the stable up approach by Bogunovic and co-authors on maximin Bayesian optimization, or there's sort of distributionally robust formulations of Bayesian optimization that have been explored by Johannes Kirschner and others in my research group, and so on. So there's lots of interesting robustness challenges that arise algorithmically in a lot of the problems that we're talking about.
Yeah, right. And I guess there's interesting combinations then as well, right?
Yes.
Yeah. Okay, so there's more questions that we should be taking. So first, general question: which direction of RL do you think is more promising, model-based or model-free? That's a tough one.
That's a tough one, in general. So, and of course, it also doesn't have to be either or, right? And there's also already quite a bit of research lifting ideas from one to the other and so on. So using model-free techniques for solving model-based RL problems and so on. I think, what is most promising? I think it really depends on what kind of applications you do want to tackle. So I think if you really want to make progress on some of the applications that we used at the beginning of this tutorial, just using black box reinforcement learning techniques, I'd be worried about. And so the question is, how can one really think about infusing the right kind of prior knowledge and ensuring certain constraints about the resulting solutions and so on. And I think lots of interesting open research questions along those lines.
Great. So there's a longer question. So it seems like many of the results hinge on well-calibrated uncertainty bounds or quantification. For example, for the uncertainty in the learned dynamics of the model-based RL. This is a major challenge to applying these results to practical robotic systems. So are there any general guidelines for practitioners to solving this in practice, or is it very domain dependent and you need custom solutions basically for each problem task?
Absolutely. So there's a lot more to say about this. It certainly is a difficult problem in practice. So here I focused a bit on the theory, what one can really do. Of course, in practice, there's a lot of research on sort of assessing calibration of different models, but also optimizing the calibration of different models, both in the context of Gaussian process models, but also other models like Bayesian neural network models and so on. So that's a big open research direction, and I don't think there's sort of well accepted standard principles that are just always applied, but sort of a lot of really active work on best practices also.
And then there's one more general question. I'm not sure if I am getting this right. It's so you point out, I think, on this last slide that scalability is one of the open problems. What other open problems do you see sort of on the horizon?
I mean, so I try to mention a few. I mean, scalability alone, you can break it down into many sub problems. So there's algorithmic components, right? How to solve these resulting optimization problems efficiently and so on, or this sort of the question of certification and so on. But then also scalability in terms of data efficiency, and that of course is a huge research topic on its own, right? How to fuse the right kind of prior knowledge. So we, for example, have been looking quite a bit recently into ideas for meta learning, sort of trying to sort of transfer observations from related tasks and learn good priors for say learn good Gaussian process priors based on related tasks that then allow to scale up more in terms of sample efficiency also. And then of course, I mean, inference problems in these models themselves are hard. I mean, it's lots of different aspects of this first bullet alone, right? So you can easily break this down into different slides. So this is certainly one big challenge, but of course also, I mean, many interesting modeling aspects, right? I mean, one thing we haven't really touched at is where do these safety specifications come from, right? That is a notoriously hard problem, right? So, I mean, reward specification in reinforcement learning is a notoriously hard problem, right? And safety specification is similarly difficult, right? Really specifying what kind of behaviors you do and you do not want, and how to encode them. What are general principles of how to do this? How can one do this? Maybe also in interaction, say with a human expert. Lots of interesting challenges. Of course, also questions where you have multiple agents that interact. How do you sort of reason about the uncertainty that comes out of this interaction, right? So sometimes you might want to anticipate certain types of reactions of other agents you're interacting with, say in the context of autonomous driving, for example, and so on, right? And I mean, all of these are big research areas on their own.
Yeah, all of them very exciting topics. So with that, I think we close here. Thank you very much, Andreas, for this wonderful tutorial and overview. We now directly go into the next session without any break. Sessions on planning and control. So it fits quite nicely to the topics that we've been discussing here. And our session chair is Aniruddha Majumdar. I'll hand over to you. Thank you.
Thank you very much, Melanie, and thank you all for joining. So my name is Ani Majumdar from Princeton University, and it was my pleasure today to be chairing the session on planning and control. So we have 3 presentations in the session. Each presenter will have 15 minutes, including questions. So if you have questions during the talk, please type those into the Q&A box. And at the end of the presentation, I will read them out, and the presenters will answer them. So the first presentation today is from Sarah Dean from UC Berkeley. So Sarah, if you're ready to share your screen, the stage is yours.
Yes, I am. Thank you very much. All right, click share. Great. Yeah, so hi, everybody. I'm happy to be presenting here today, especially after such an apt tutorial by Professor Andreas Krauss, talking about sort of safety and reinforcement learning and in machine learning. So today I'm talking about this paper called Guaranteeing Safety of Learned Perception Modules via Measurement Robust Control Barrier Functions. And this is joint work with my collaborators, Andrew Taylor, Ryan Cosner, Ben Recht, and Aaron Ames at UC Berkeley and at Caltech. So this work is really motivated by the fact that, you know, in our increasingly digital world with a variety of digital technologies, robotic systems have the ability now to use increasingly complex sensors, whether it's cheap cameras, because camera sensors are cheap, or more advanced sort of imaging sensors and depth sensors. So vision in particular kind of motivates this work. And it's a complex sensing modality that is not as straightforward as our traditional sensors. But at the same time, it's very valuable and can provide a lot of rich information about the scene and about the state of a system. So because these sensors are more complex, they require more complex calibration routines. So this is sort of maybe a familiar picture of like a ROS camera calibration routine. But in general, doing this kind of calibration might require something data-driven or use some kind of learned model. And this leads to opportunities for measurement model error. And that can have sort of dire consequences if we want to take our systems out of the lab and put them into the world. So this picture here is from a National Traffic Safety Board report on a crash of a Tesla driving on autopilot on the 101. So sort of local to me. And basically what happened in the crash is that the car failed to sort of detect that it was in this space between to the exit and the highway and remained sort of in this dead space until it hit the barrier. And so it's sort of important that, yes, cameras provide a lot of great information, but how can we make sure that they're safe and effective for controlling a system? So In this work, I'm not going to try to solve all of self-driving cars. That might be a little too much, but I will consider the setting of nonlinear control affine dynamics. And I'll suppose that these functions f of x and g of x are known ahead of time because the system is sort of well specified. It's a robot that we built. Now, to consider safety, I'll define this set C as this zero superlevel set of some function h. And this is just some subset of the state space. And I'll suppose that what we mean by safety in this setting is the invariance of this set C. So the system must remain in this set for safety to be guaranteed. And this is not a probabilistic notion of safety. This is sort of very deterministic. What makes the system different, what makes our setting different from a more traditional sort of nonlinear control setting is that the system is observed by some complex function, p of x, which gives rise to observations y. So for example, we might have a robot, which rolls around it and has different angles and different speeds, which is observed through a camera, which gives rise to some observation, which may be some image. And then to sort of understand the state of the system, we will back out some estimated state x hat from a function q. Q hat, which I'll refer to as either an approximate inverse, so it's approximately trying to invert this mapping P. I'll also call it a perception map because it's sort of perceiving the system state from an image. So before we get more into this observation model, let's go through safety. So how does one maybe guarantee safety, or what are some ways to do it in these nonlinear systems? We actually just had a great review of that. I'm going to focus on this method using control barrier functions. So remember this function h, which defines our safe set. It will be called a control barrier function if there's some extended class K function alpha such that the following inequality holds. So looking at this inequality, it says that this sort of inner product between the derivative of h with respect to the state and sort of the system dynamics is bounded below basically by some negative value. And if we want to sort of draw a picture, it looks a little bit like this. So we sort of have it, the way the system evolves, the direction of system evolution is pointing inwards at the boundary of the set. That's a nice way to think about it. Basically what we're doing with this condition, what we're asking H to be, is to ensure the existence of some control action U such that, right, this state evolution multiplied by the derivative is bounded below. In other words, that the derivative of H itself with respect to time is bounded below. And really what this means is that by choosing a U such that this property is satisfied, we're ensuring that H remains positive. And recall by definition of our safe set, this shows that the safe set is invariant under that trajectory. So that's why this is a great way to ensure safety. And this is the framework that we're going to use. So sort of this specifies how we want to think about choosing control actions. It allows us to define a set of inputs for each state, which will help the system to ensure safety. And we can actually use this as a safety filter for any given controller, either hand designed or maybe a learning controller, can be filtered using a convex optimization problem because this condition on our control input U is actually this linear constraint. And I also want to point out on this slide, I'm going to start using this Lie derivative notation. So LF, the Lie derivative of H here is just this product. And that's just for simplicity. Yes. So that was great, and this is sort of a known way to keep systems safe, but it relies on knowing exactly how the system will evolve. If you don't observe the system state directly, that's something that you can no longer predict perfectly. So our setting has this imperfect state observation, which is the problem. There's actually some related work that considers slight variations on this, where the state is also imperfectly observed due to things like noise. And it's not exactly what we'll be doing here, but they give rise to sort of similar conditions. So since we don't know what the state is, we're left with sort of reasoning about possible states given what we've observed. And so given an observation Y and sort of doing this perception map that might be imperfect to have an X hat, And then supposing there's some errors there, we get this set of states in state space, which sort of this calligraphic X of Y. And now instead of trying to ensure this control barrier condition for the single X, we have to try to do it for all X's because we don't really know where we could be. So what do I mean? Like, what does the set actually look like? So recall X hat here is given by this Q hat of our observation. And so if there is some true inverse, you can sort of rewrite the equation this way and see that really we're just observing the state plus some error. So this is our perception error, E of Y. And that's what I'll talk about, because this sort of defines, a set might be centered on this X hat and its radius is determined by this E of Y. And so supposing that that perception error is bounded, we can now sort of rewrite this barrier condition, this robust barrier condition, as follows, where we're now sort of minimizing the left-hand side over all possible errors. This is not really an easy expression to work with because those lead derivatives are certainly going to be nonlinear. Remember that we were trying to use this condition as a constraint and optimization problem, so it sort of ended up get this like max-min kind of condition, so it's not great to work with. So we'll do sort of a robustification. And that motivates our definition of measurement robust control barrier functions. And so we define a set of inputs which ensure robust safety as follows. So looking at this condition inside the set, the difference from the sort of traditional control barrier function condition is this additional negative term on the left-hand side. And this is for some given functions A of Y and B of Y, so functions of our observation, which will be positive. And we have this multiplication by the norm of the control input. This term captures the uncertainty in our system that arises because of our imperfect observations. And so combining this with some of the intuition from the previous slide, we have this result that as long as we can bound the system's perception errors by some epsilon of Y, so a scalar value epsilon, and the lead derivatives and the barrier function are Lipschitz, then by setting A of Y and B of Y as follows, sort of depending on the continuity and on those perception errors, any controller inside this robust safe set will render the system safe. So we have now a way to constrain the system, or to constrain our control inputs that will guarantee robust safety. And now we can use this in an optimization problem to use a similar sort of safety filter. So comparing this to our previous control barrier function problem, we're now sort of doing the same, trying to stay close to a given desired controller with a constraint now which has that extra term. And inspecting this, this is a second order cone program because of that norm of U that shows up in the constraints. But it's still a convex problem and therefore can be solved efficiently. One question to ask, though, is this actually feasible? So the feasibility of the normal control barrier function optimization problem is guaranteed by the definition of control barrier functions. And here, it's not necessarily going to hold anymore, but we can ensure its feasibility if the errors are small enough. And in the paper, we go into a little bit more detail on this, but making those errors small under different measurement models can be done from data. So essentially by sort of densely sampling within that safe set, you can guarantee that your errors are small enough to ensure feasibility. I'll also point out that the errors don't have to be that small because this problem can still handle some sort of non-negative errors, which means that your system can remain safe even with imperfect observation. So I'll just wrap up by sort of motivating that this can work at least in a simulated system and show how useful it can be to add this robustness. So the system I consider is a Segway robot constrained to planar motion, which means it moves only forward and back, and that safety will be defined by its pitch angle. So we just don't want this robot to fall over. Specifically, it's defined sort of by this set in pitch angle and pitch angle rate space. And to sort of match our perception setting, we'll say that the pitch angle and the position are not accessible by anything but some camera image. So there's many ways you could try to sort of back out the position from the image. We're just going to go full on machine learning and just do it from data. So training data, 800 training images were collected from a grid of different angles and different positions. These are some examples. And a model mapping the image to the position and angle was trained with sort of this non-parametric ridge regression with radial basis functions. And on a held out set, it actually performs fairly well with sort of errors around 0.1 or 0.2 radians, at least in angle. And so I'm running out of time, but I'll just show that without, in closed loop, with just a standard safety filter, the system actually does not remain safe and leaves the safe set. Although it does ultimately come back, the safe set is not invariant. And so we failed to satisfy the right property. However, with the robust condition, we are able to stay in this set regardless of the perception errors that we have. And that's what this demonstrates. So in conclusion, we propose measurement robust control barrier functions, which can ensure safety. They're a convex optimization problem, and it depends on system continuity and boundary perception errors. Thank you.
Thanks very much, Sarah. So yeah, if the audience has any questions, please type them into the Q&A box. We might have time for one question, I think. And maybe as we're waiting, I'll ask a question of my own. So if I understood the architecture correctly, it looks like the perception module is trying to reconstruct the full state of the system. And I wonder, for a lot of problems, that may be unnecessary. So the state might contain information that's not task relevant. So I wonder how your architecture deals with that.
Yeah, so I think really as long as you can guarantee safety, as long as whatever your safety condition is, like only depends on that subset of the state, then I think it would sort of fit directly into this framework where you might have sort of like a lower level controller that deals with like accelerations and torques, and then your high level controller is just on position. I think that's like a good example of where this fits in directly. On the other hand, if you really do need to reason about sort of like velocities and you can't measure that from your camera sensor, then that's a reason to extend this into sort of a state estimation setting.
Thank you. All right, it doesn't look like we have any questions so far. Yeah, maybe I'll just remind everyone, I guess if you don't get a chance to ask a question here, the authors will be available at the parallel interactive sessions later today. So you can ask your questions then. All right, so our next speaker is Marcus Pereira from Georgia Tech. So Marcus, whenever you're ready, the stage is yours.
Thanks, Ani. I just wanted to verify, can you see my slide? It's just an empty slide. Sorry, a slide with the title of my presentation.
Yes, but I think you might be in presenter mode. We see your notes as well.
Oh, I see. Okay. Sorry.
It's still in presenter mode.
Maybe I should try to share screen again. Oh, sorry. How about now?
Yes, looks good.
Thank you so much. Thanks for the patience. Okay, so good morning, everyone. My name is Marcus Pereira, and I'll be presenting our work on safe stochastic optimal control using barrier functions and deep forward-backward SDs on behalf of my team at the Georgia Institute of Technology. In this work, we propose a novel algorithm for safe reinforcement learning, an architecture to solve constrained Hamilton-Jacobi-Bellman equations that ensures safety not only during testing, but also during training. That is end-to-end differentiable, and that combines the principles of safety and optimality into one framework under uncertainty. We achieve this by bringing together stochastic control barrier functions, deep forward-backward SDEs, and the OpNet differentiable convex optimization layer to produce an end-to-end differentiable safe stochastic optimal controller. Thus, our work lies at the intersection of three very important fields in robotics research, namely safety, stochastic optimal control, and end-to-end deep learning architectures. We guarantee safety through SCBFs, optimality through deep FPSDs, and end-to-end differentiability through the OpNet layer, thus giving our framework. Before we take a closer look at each of these building blocks, let us quickly look at the problem statement. We assume that we are given control-affine nonlinear system dynamics, where X, U, and W are system state, controls, and Brownian noise vector respectively, and F, G, and sigma are the uncontrolled dynamics, actuation, and covariance matrices. We are also given a cost function that defines the task to be completed within a fixed time horizon. This cost function is comprised of a running state cost, a quadratic running control cost, and a terminal known cost function phi. We are also given a barrier function that is task specific and hand designed, and a safe set that is a super level set of this barrier function. Also, the boundary of this set is where the barrier function is identically 0. Finally, we also assume that we start inside the safe set. Now, we can define the value function as the minimum cost incurred starting from state X and time t. Notice that this is a constrained minimization problem, as the only admissible controls are those that ensure that the state is inside the safe set for the entire time horizon. Then, using Bellman's principle of optimality, one can easily derive the HAB PDE by simple application of Ito's formula. Because of a given terminal condition, the HAB is a backward PDE, and it suffers from the well-known curse of dimensionality. Now, this can be tackled with well-known non-sampling-based methods such as STDP-Galerkin approximation, or sampling-based methods such as the path integral control framework, or FPSDs. We focus on FPSDs as it is the most general of these frameworks. We start with the first building block, stochastic CBFs. These extend deterministic CBFs to stochastic dynamical systems. We define a zeroing stochastic CBF as any function h that defines a safe set and guarantees safety if for some class k function alpha, the following inequality holds for all time. We refer to this as the safety constraint. Now notice that the left-hand side of this constraint is the Ito time derivative of the barrier function in contrast to the regular time derivative in the deterministic case. Using the above definition, we can now state the following theorem. Assuming that there exists a control u of t prime such that for all t prime less than t, the above inequality is satisfied, then the process x of t has remained inside the safe set with probability 1. The proof of this theorem is available in the appendix of our paper. Next, we look at deep FPSDs, which are deep learning architectures that solve general parabolic partial differential equations. This is achieved by application of the so-called nonlinear Feynman-Cach theorem that links the unique solution of PDEs to systems of FPSDs. The HAB PDE that we just looked at, that is in fact a parabolic PDE. Now, applying the nonlinear Feynman-Cach theorem to the HAB PDE yields the following system of FPSDs, wherein the forward SDE is the system's dynamics, and the backward SDE is the value function process. Why do we care about deep FPSDs? That is because they simplify solving systems of FPSDs. The main technical difficulty in solving FPSDs is that the backward SDE is technically difficult to solve. This is because solution of the backward SDE requires backpropagating conditional expectations in order to get adapted solutions. And this method traditionally has been known to be prone to regression errors and therefore cannot scale. Now, deep FPSDs, on the other hand, they allow forward propagation of the backward SDE by casting it into a simple deep learning problem, as we shall soon see. Finally, we look at the third building block, which is the OpNet differentiable convex optimization layer, which generalizes a neural network layer as a solution to a quadratic program. In the forward pass, an interior point solver outputs the solution to the QP. The inputs to this layer could come from regular neural network layers or from other OpNet layers. Now, in the backward pass, one simply differentiates through the KKT conditions evaluated at the solution of the forward pass. This is very efficient. It does not require automatic differentiation through the unrolled graph of the QP solver, which would then make application infeasible for high dimensional problems. Now, these gradients can be computed with respect to any of the layer parameters. Finally, why do we care about the OpNet layer? That is because deep FPSDs require differentiability of all its subcomponents, and the OpNet allows embedding argmin QPs into the deep FPSD framework. Putting all of these components together, we have the forward SD systems dynamics, the backward SD value function process. These are handled by deep FPSDs. We have a QP at each time step to solve for the optimal control and safe control. This is handled by the OpNet layer. And finally, the safety stochastic CBF constraint inside the OpNet layer. We now look at our proposed deep learning architecture. We are given an initial state, and we know a terminal cost function that allows us to compute the value function and its gradient at the terminal time step. However, we want to avoid backpropagating the backward SD, but the initial value is unknown. So therefore, we just make this initial value as a trainable network parameter. And in fact, the known terminal value and its gradient now become prediction targets for this deep network. Remember how I said that we can now forward propagate backward SDs? This is how we do it. We then initialize the weights of the network. We use the network to predict the gradient of the value function at the initial time step. This in turn is used to forward propagate the value function with sample noise. This gradient is also fed back into the OpNet safety layer to compute a safe control. The safe control is used to forward propagate the system's dynamics with noise. Now the new state is fed back into the LSTM and is used to predict the gradient of the value function at the next time step. We now repeat this process of forward propagating the value, computing a safe control, and forward propagating the system state. And we continue this process until the end of the time horizon. Finally, using the known targets and the predicted value and its gradient, we compute a loss function. And then using any stochastic gradient descent variant, we can train the weights of this network. For all our simulations, we used the following stencil to construct barrier functions. The position constraint of the stencil, it defines the task and is task dependent, and it defines the original safe set. For example, suppose we want to avoid an obstacle, then this position constraint would literally mean the distance from that obstacle. It would be strictly positive away from that obstacle and 0 at the obstacle boundary. However, notice the squared velocity term. Because of the addition of the squared velocity term, we have the following implications. The first is we create additional boundaries, and it modifies the original safe set. Adding this term would mean avoid certain positions at certain velocities instead of just avoid certain positions. Also notice that because at the boundary, the position constraint becomes 0, the only allowable safe velocity at the boundary is 0. And that means the system has to slow down as it approaches the boundary. The other implication is that the relative degree of this system, of this barrier function, is 1. As a result, the lead derivative of h is not 0, meaning we can use control to satisfy and enforce the safety constraint. Let us consider a simple scalar example for intuition. Suppose that the safe interval is -1 to 1, and our position constraint would look like so. Then, as I increase mu from 10 to 1 to 0.1 to 0.01, notice the size of this ellipse keeps growing. That means the allowable safe velocity at the center of the interval keeps growing. Thus, one can tune mu to allow more aggressive behavior inside the safe set. Now we present some highlights from our simulations. We start with the cart pole balancing task with a time horizon of 1.5 seconds. The initial position is the vertically upward unstable equilibrium position, and the goal is to stabilize around this unstable equilibrium position. For comparisons, we use unsafe deep FBSDs, and then we progressively increase the difficulty of the problem by first imposing only pole angle constraints and then both pole and cart position constraints. In the video alongside, the gray boxes are cart position bounds, and the red area represents unsafe pole angles. As seen in the video, initially the unsafe controller completely violates both bounds because it is simply blind to both bounds. Then next, we impose only pole angle constraints. Now notice the cart can save the pole from falling by moving very fast in one direction, but however, this violates the cart position bounds. Finally, we impose all constraints, and now the cart is able to stay within the bounds and save the pole from falling as well. for the entire time horizon of 1.5 seconds. At the end of the day, they all learn the same policy, and therefore we reiterate the need to stay safe during the entire learning process. For our next example, it consists of 4 2D cars, each with a nonlinear kinematic model, starting at 4 corners of a square grid as seen. And the task is to swap positions with the diagonally opposite car while avoiding collisions. For this task, we used 4 choose 2, that is 6 barrier functions for each car pair. And the barrier functions were based on the same stencil that we saw earlier. As seen in the video, initially the cars moved towards the center and they stopped short of their targets. However, these states get associated with a high cost or high value and therefore are non-optimal. Therefore, as seen, the cars try going around the targets to avoid these non-optimal states. As iterations progress, the controller tries to strike a balance between optimality and safety. Finally, they all learn to move towards the center, orbit around the center, and then gracefully move towards their targets. In conclusion, we introduced a general framework for safe learning control grounded in first principles by leveraging connections between FBSDs and nonlinear PDEs. We employ stochastic barrier functions to guarantee application of safe control at each time step, and utilize OpNet's efficient gradient computation to make this entire framework end-to-end differentiable. Due to the general applicability of the nonlinear Feynman-Cach theorem, one can consider many theorems, many algorithms emanating from this work. To name a few, mean field games, L1 stochastic control, and others. Finally, this work is also a stepping stone for more complex safety critical applications, such as aerial and robotic and space vehicle navigation. We would like to thank NASA and NSF for sponsoring this research. Thank you for listening, and I would love to take any questions if you have any.
Thanks very much, Marcus. Yeah, any questions from the audience, please type them into the Q&A box and I will read them out to Marcus. All right, we have a question. So the question is the approach going to be open sourced? So the software and the code for the approach, is it going to be available on GitHub or an open source platform?
Thanks for asking that question. Yes, we are definitely working on making a public repository for that, and we will try to also have instructions on replicating all of our experiments.
Thanks. All right. One more question. So thanks a lot for the great talk. This is from Sushant Veer. Could you comment on the scalability of this approach for vision-based tasks? So maybe scalability in terms of sample complexity and computation as well.
That's a very important question. In terms of scalability for vision, we could consider different approaches, such as we have also worked on belief space deep FBSDs that tries to incorporate observations and observation noise. But if you go and look at some of our published papers, we have shown the deep FBSD framework to scale up to 100 dimensions and above. For example, on portfolio optimization problem where the dimensionality comes from the large number of stocks processes. So we have definitely shown examples in the past, and we are working in that direction to now scale this to complex models in simulators.
All right, thank you, Marcus. Okay, so our next presenter is Rohan Chitnis from MIT. So Rohan, whenever you're ready, the stage is yours.
All right, can everyone see my screen and hear okay?
Yes, looks good.
Okay, great, so I'll get started. Hi everyone, my name is Rohan. I'm gonna be talking to you about our work on camps, learning context-specific abstractions for efficient planning and factored MDPs. So it should hopefully be intuitive that for any decision-making agent, when it has a lot of options or like a lot of choices as to what it can do, this can result in taking a long time for it to actually make any decisions or plan out its actions. This is very, very common issue in robotics. So for example, consider this navigation among movable obstacles NAMO task shown here, where the goal is just for the robot in the bottom left to get to the location in the top right, marked in red. If you try to use a kind of general purpose planner for the setting, it can be very slow just because of the number of options that are available here. For example, which rooms should the agent go through to try to reach the goal? Which objects should it move out of the way? When should it move those objects? How should it control itself to be able to follow the path that it thinks of? We can also say very similar things happen in manipulation settings. So consider here a problem where the goal is to move these red objects from the table on the left into the empty bins on the right. We can make a very similar statement here, which is that if we were to try to use a general purpose planner, which doesn't leverage any specific heuristics about this problem or domain, then it can be very slow just because of the many options available to the agent in these continuous spaces. So basically, if we acknowledge that planning suffers when too many choices are available, what we're interested in this work is following a long line of related literature that addresses the question, can we basically find a way to narrow down the space of choices that our planners have to consider? And so you might be thinking an extreme solution would be, why do we have to do planning at all? We should learn a reactive policy, right? A mapping from states to actions, and then we can just kind of follow that policy once we've trained it. And that's great, right? We don't have to plan. This is definitely true, but it does have its downsides. Learning a reactive policy can be very expensive to learn in terms of data efficiency. It can cost a lot to acquire the necessary data. And furthermore, it's kind of unlikely for such a policy to generalize well in the kinds of settings we are interested in this work, which are long horizon, continuous robotic planning problems. Very hard to get a policy to actually perform well in such problem settings. So we can already say that what we're really interested in here is optimizing a trade-off, which hopefully you all find to be intuitive. So supposing we have a task omega marked in blue, what we really want at the end of the day, I hope everyone agrees with this, what we really want at the end of the day is that we want a policy that performs well at whatever that task is, but also it doesn't take the robot too long to actually come up with that policy. So if we think about this objective, what we really want is a kind of sweet spot between two extremes, right? So on one extreme, we have let's just plan for that task that we're given. It's likely to get good rewards because you're kind of intuitively considering all the different possible options. That's like what planning is, right? But on the other hand, it's going to cost a lot to actually come up with the policy that achieves that high reward. On the other extreme, we have policy learning. So say we already have trained a policy on some different tasks. Using that policy for this new task omega is unlikely to be very expensive, but if it fails to generalize well, then you'll see it suffer in terms of reward. So in trying to find a sweet spot for that objective, the first key idea of our work here is that we should make use of constraints, right? Constraints simplify planning because they basically guide the planner. And so the first key realization is that agents can actually impose constraints on themselves for the sole purpose of making planning more efficient. So these aren't physical or environment or safety imposed constraints. These are constraints that the agent chooses for itself. So let's look at an example going back to the NAMO example. We could say that maybe the robot might only consider paths that go through these rooms. And the reason that this would be help a planner is because now the planner doesn't have to consider paths that go outside of these rooms marked in yellow. We can say a very similar thing in the manipulation case. We can maybe the robot could constrain itself to only consider certain ways of grasping the red objects, like top grasps only, and only consider placing into certain bins. So the next key idea, which is actually the main novelty of our work, is that these constraints can actually help in an even greater way. Not only do they help guide the planner, but also they can make aspects of the problem irrelevant. So the key piece of formal machinery we use here is the notion of context-specific independence. This is due to Boutlier from 1996. This is a notion that can't actually be expressed with a classical Bayes net. And it basically is conditional independence of two variables, but conditioned on specific assignments of other variables. So a simple example would be, if I am in the context or the constraint that I am staying inside my house, then the outfit that I choose is going to be independent of whatever the weather might be outside. So we can make use of this going back to our example. So we've already seen that maybe the robot says, okay, I'm only going to stay in these rooms marked in yellow. But the context-specific independence lets us go a step further and then remove these other objects from the planning problem, therefore simplifying planning. We can also say a similar thing for the manipulation case. So here, if the robot chooses to only grasp these red objects from the top, then it doesn't run the risk of its gripper colliding with these blue objects here. And similarly, if it only places in these bins here, it doesn't run the risk of its gripper colliding with these green objects here. So we can say that these objects become irrelevant. So it's really important to realize that these blue and green objects are not like always irrelevant to this problem instance. They're only irrelevant because of the constraints, that the robot imposed on itself, that it's only going to top grasp and only going to place in certain bins. So now we're ready to kind of put everything I've talked about together. And so here's what a CAMP is, context-specific abstract MDP. So if you're given a factored MDP and a particular constraint on your states and actions, then a CAMP is like an abstracted version of that MDP. So the first thing it changes is that violating the constraint leads to an infinitely negatively rewarding absorbing sync state. So basically, please don't violate that constraint. And the second thing is that we can make use of the context-specific independences I mentioned to remove things that are irrelevant under that constraint. So hopefully from these two things, you should be able to see that planning in a CAMP is usually going to be a lot faster than planning in the original MDP. You have a simpler MDP to plan in. Of course, this does come at the cost of reward optimality, but as we mentioned before, we're interested in this trade-off objective where we don't necessarily need the highest reward policy, but we really care about the speed that the amount of computation basically that's required to obtain the policy that achieves that reward. So at this point, you might be wondering, okay, this is all great, but how do we actually do this stuff? So for example, how do we actually figure out what factors here are irrelevant under the constraint? And where does this constraint even come from? How do we know what constraint to decide on? So these are good questions. And to answer those, we kind of set it up as a learning problem. So very broadly, we're imagining we have a multitask setting where you have a bunch of training tasks that all have a shared transition model. And from these training tasks, you can learn these two things that I mentioned. So the first thing you can learn is what are the context-specific independences that hold in this transition model, so in this domain, basically. The way we do that is we approximate it with Monte Carlo estimation. And the second thing that we learn is a constraint selector, which is basically a neural network that's conditioned on the problem instance. So it takes in the initial state and information about the reward. And it's a multi-class classifier, and it predicts basically what constraint is the best one for the agent to impose on itself. So just to kind of summarize everything I've talked about here, remember that the objective we care about is this trade-off between reward and computational cost. So if we were to apply just a planner on our tasks, it's likely that the planner would be able to solve the tasks, but it might take a long time for the planner to come up with a policy that does so. Policy learning would be another approach. If you have your policy trained, it's very fast to do inference with that policy. But if it didn't generalize well, it's unlikely to perform well in terms of reward. So we see CAMPs as a kind of sweet spot. So what we're going to do is we're going to have our problem instance. We're going to use our context selector that we've learned to pick a particular constraint or context that the agent should impose on itself. We use our learned context-specific independences to figure out what aspects of the problem became irrelevant. Now we have a CAMP that we can plan in. It's a simplified version of the full MDP. And then we can apply the policy that comes out of our planner on the original problem. So this is going to provide a good sweet spot in terms of the objective we care about. So experimentally, we tried CAMPs in many different domains, from robotics to classical planning to grid worlds, with several different planners as well, from task and motion planners all the way to classical things like value iteration, graph search, that stuff. Across all these domains, we found that CAMPs generally allow for fast and rewarding planning, so a good sweet spot like we've been talking about. So here what these graphs show is on the y-axis you have returns in the environment, and on the x-axis you have computational cost. So up and to the left is better. And so these blue dots, which are CAMP, basically you can see that across all of these problem settings that we consider, CAMPs tend to perform very well. A particular result that I wanted to highlight is that we were able to find that CAMPs actually outperform Stillman's NAMO-specific planning algorithm without any NAMO-specific reasoning. So what's really cool is that camps are able to perform well on our trade-off objective without actually having a specialized heuristics for each of these different problems. It's a very general approach that you can apply to many different kinds of problem instances. Now just to show some videos of the behavior. So here is the navigation example we've been talking about. So here it's kind of planning, and now it's going to execute the policy. So you could see that while it was planning, it ignored all of these objects in these other rooms here. And now while it's executing its policy, you'd better hope that the policy that it's following here actually obeyed the constraints that that it was using while planning, right? Which is that it only stays in these in certain rooms here that were marked in yellow. We can also see a video for the manipulation setting. So again here, as we talked about before, the agent is only constraining itself to use top grasps on these red objects, which is why you see that it's only going to pick things up with a top grasp. This allowed it to simplify its planning problem by not having to consider the blue and the green objects. But what you see is that as a result of doing a top grasp, the agent realized that because it has to use a side grasp to place the objects in bins, it actually needs to do this little handoff procedure where it changes its grasp on the object before placing it into the bin. I also want to note here that, that this fact that these blue objects became irrelevant as a result of using only top grasps on the red objects, that's not something that we told our system, right? This was something that was learned on the training tasks by our learning approach. So yeah, hopefully you find that to be a cool result. And that's about it. So with that, our code is available on this GitHub URL. So feel free to check it out if you're interested. And we'll also be at interactive session number 3 today. And at this point, I'm happy to take any questions.
Thanks very much, Rohan, for the great talk. I think we have a couple of questions. So the first question is from Sushant Veer. So in general, how would you ensure that the imposed constraints do not violate the solvability of the task?
Yeah, great question. The answer is that, like, theoretically, you absolutely, we can't. So nothing in our problem statement stops you from being able to impose a constraint that says, I'm never going to leave my house if the goal is to get to the grocery store. But remember that we are learning a model that is going to predict what would be a good constraint to use. And that model is trained to select constraints that optimize our trade-off objective that I keep talking about. So if you aren't getting any reward from using a particular constraint, the value of your objective will be very, very low because you should be having a policy that uses. Now, one thing to note is that if you crank up the term, so that policy is a trade-off, right? Sorry, that objective is a trade-off. If you crank up the term really high on the second term, which is just like how long does it take to compute, then you're actually always going to pick constraints that just say, I'm just going to stand here and do nothing ever, because that requires very little thinking. It's never going to get me any reward for any task, right? But so the weight that you put on the trade-off between these two terms and the objective does actually matter.
Thanks. And I think there's another question from the audience. So how do camps fare in non-stationary environments, such as the multi-agent navigation setting?
Yeah, so I think one issue that arises in non-stationary environments with respect to what we're doing here is one of the limitations of the current approach is that we only consider a single constraint or context to be imposed on the agent for the entire episode. Now, if there's non-stationarity, or to be honest, even if there isn't non-stationarity, but in certain situations, it can be useful to change your context or your constraint as the episode continues, right? So the constraint you impose at the start may not be the constraint you want to impose later on. So this kind of suggests a more interesting, an interesting direction for future work, which is to bring in the notion of sub-goals into this whole thing, right? So so to address the non-stationarity question, I would imagine that maybe a good way to handle that would be if you have kind of a sub-goal at any given time, and as there's non-stationarity in the environment, things may change. You may decide, okay, my current sub-goal is no longer worth pursuing, or maybe you've achieved it. Now I'm going to move to the next sub-goal, and I want to generate a new camp for that sub-goal. And that's something we don't do right now.
Awesome. Yeah, thank you, Rohan.
Thank you.
Yeah, so I think that concludes our session on planning and control. So yeah, thank you again to all the speakers, and thank you all for attending. So we now have a little bit of a break in the program. So the conference program will resume in about 7 minutes with the parallel interactive sessions. Thank you.
And we're going to close this webinar in a couple of minutes, but we hope to see all of you back in about 2 hours for the panel on grand challenges in robotics.